There is a moment in every great discovery when the people who made it stop talking. Not because they have nothing to say, but because what they are looking at is too large to fit inside the words they brought with them. On a quiet morning in Baltimore, in a sealed control room lit only by monitors, a small group of astronomers stood in front of a screen and waited for an image to load. They had spent decades, in some cases entire careers, preparing for what was about to appear. They expected light. They expected stars. They expected to feel the satisfaction of seeing the early universe finally pulled out of the dark. Instead, the image arrived, and the room emptied of sound. What they saw was not the soft, faint, uncertain glow of a young cosmos. It was a city. Or rather, it was thousands of cities, each one a galaxy, each one impossibly old, impossibly heavy, impossibly bright. The image had captured a slice of sky no bigger than a single grain of sand held up against the night, and inside that grain, an entire civilization of light was waiting. The light had been traveling for 13 billion years, and in that long, patient journey, it had carried with it a message that none of the textbooks on the shelves below the monitors had ever predicted. The message was simple, and it was devastating. The universe is older than its story. The universe is faster than its physics. The universe, perhaps, is something we have not yet understood at all. Tonight, you are going to travel with that light. You are going to follow it back through every layer of cosmic history we thought we knew, into galaxies that should not exist, into black holes that grew before they had any reason to grow, into the chemistry of stars that died before the first stars were born. You are going to stand at the edge of a planet whose atmosphere may be quietly whispering the word that humanity has spent its entire existence waiting to hear. You are going to discover why a single telescope, floating 1.5 million kilometers from Earth, has done something no other instrument in history has ever done. It has cracked the foundation of cosmology, and it has done so politely, calmly, one image at a time. Settle in. Let the room around you grow quiet. The story you are about to follow is not a list of discoveries. It is the slow, careful unraveling of a worldview. And if you find yourself drifting somewhere along the way, drifting between stars, drifting between hours, that is exactly where you are meant to be. Because the universe that James Webb is showing us was never quiet. It only seemed that way until we built an eye large enough to listen. Before any of this could happen, before a single photon could be measured, before a single galaxy could be weighed across 13 billion years of distance, a machine had to be built that could survive the impossible. The James Webb Space Telescope is not a single object. It is a careful argument made out of metal and glass, a proposal written in beryllium and gold, a question phrased so precisely that the cosmos has no choice but to answer. Its mirror is not one mirror. It is 18 hexagonal segments, each polished to a smoothness that would, if scaled to the size of a continent, leave hills no taller than a fingernail. Each segment is coated in a layer of gold so thin you could not see it as a sheet, but spread across the whole structure, it gives the telescope its strange, honey-colored gaze. The mirror does not collect ordinary light. It collects infrared, the wavelength of warmth, the wavelength that ancient light slips into when it has been stretched by the expansion of space for billions of years. Visible light, the kind your eyes know, gets tired on long journeys. Stretched far enough, it becomes invisible to us, fading into a part of the spectrum that human evolution never bothered to learn. James Webb learned it. James Webb was built to see exactly the light that everyone else missed. That light, however, is faint, almost shy. To catch it, the telescope had to be cold, not cool, not chilled. Cold the way the deepest shadow in space is cold, somewhere near the temperature where atoms themselves begin to forget how to move. To achieve that, the engineers built a sunshield the size of a tennis court, made of 5 layers of a material thinner than a human hair, designed to reflect every photon of warmth coming from the sun, the earth, and the moon. On one side of the shield, the telescope sits in eternal twilight, colder than almost anywhere humanity has ever measured. On the other side, the shield itself faces a constant blast of solar heat. The temperature difference across that thin barrier is greater than the difference between a winter night in Antarctica and the surface of a desert at noon. Yet the membrane holds. After launch on Christmas morning of 2021, the telescope unfolded itself in space across nearly a month of motions so delicate that no one watching could quite breathe through them. 344 single points of failure. That is what the engineers called them. 344 moments where one stuck pin, one wrong angle, one thread of unfolding film could end the mission and erase a generation of work. None of them failed. The mirror unfolded. The shield bloomed. The telescope traveled to a quiet point in space called the second Lagrange point, a gravitational eddy where the pull of the sun and the earth balance so gently that an instrument can sit there with very little effort, drifting along Earth's orbit like a child held by 2 parents. From that perch, James Webb began to look, and what it began to see, almost immediately, was something nobody had been ready for. The first deep field image, when it was finally released to the public in the summer of 2022, looked at first glance like an old friend. Hubble had given humanity images like this before, dotted with galaxies, glowing across long exposures. But this image was different in a way that took a moment to register. Where Hubble showed soft, blurry shapes near the limit of its vision, James Webb showed clean, sharp galaxies all the way to the edge. There was no edge of fading. The galaxies just kept going, smaller and farther and older, and at every depth they remained crisp, defined, undeniable. Astronomers had a word for this feeling. They called it a wall of light. The early universe, when seen with the right eyes, was not empty. It was crowded. It was loud. It was busy. And as those first deep galaxies were measured one by one, an unsettling pattern began to emerge. They were not dim. They were not small. They were not the gentle infants the Standard Model had promised. They were already, somehow, something else. To understand why this matters, you have to picture the universe the way astronomers thought it had to be. For most of the last century, the story of cosmic history had a comforting shape. After the Big Bang, the universe was hot, dense, smooth, and dark. It cooled. The first hydrogen formed. Gravity began to pull tiny irregularities into clumps. Slowly, over hundreds of millions of years, those clumps grew. The first stars eventually ignited inside the densest regions, scattering light into a cosmos that had not yet learned what light meant. Galaxies formed, but they formed gradually, awkwardly, in fragmented pieces that took many cycles of merging and reshaping before they learned to look like anything familiar. By the time the universe reached around 500 million years of age, the textbook said, you would expect to see small, irregular, faintly glowing structures. They would be roughly the size of dwarf galaxies. They would contain only a modest amount of stellar mass. They would be chemically simple, made mostly of the lightest elements left over from the early universe. Anything more advanced than that would have been physically impossible. There simply had not been enough time. James Webb pointed at that exact era, and what it found was almost the opposite of expectation. There were galaxies in that period whose mass alone was startling, sometimes carrying the equivalent of tens of billions of suns' worth of stars, packed into structures that should not have had time to form 1/100th of that. There were galaxies whose brightness suggested star formation rates running not at the gentle pace of an early stellar nursery, but at a fevered, almost industrial intensity, churning out new suns at speeds that modern galaxies cannot even approach during their busiest moments. There were galaxies that already showed signs of central concentration, hints of the disks and bulges that take billions of years to settle. And the more astronomers looked, the more such galaxies appeared. They were not exceptions. They were a population. The first papers describing this came out cautiously, the way scientific papers usually do when something is too large to claim outright. But behind the careful language, the implications were enormous. Either the standard model of cosmic growth was wrong, or the timeline of the universe needed to be reconsidered, or the very rules by which gas turns into stars had behaved differently in the early universe than they do today. None of those options were small. Each of them, in different ways, would require rewriting parts of physics that had been considered settled. Some scientists tried to find errors in the data. They suggested that some of the apparent masses might be inflated by the presence of bright accreting black holes confused for star clusters. They proposed that dust might be muting certain wavelengths and biasing the analysis. They noted that distance measurements at such extreme scales depend on assumptions that themselves could be revisited. All of these explanations softened the problem. None of them dissolved it. Even after the most cautious corrections, a stubborn population of early galaxies remained that no model could comfortably accommodate. They simply existed. They simply shone. They simply behaved as though they had been forming far longer than the universe had granted them. One astronomer, after months of cross-checking, summarized the situation in a quiet sentence that has been quoted many times since. He said that the universe seemed to have skipped its childhood. That phrase carries weight. A child does not become an adult overnight. Trees do not grow centuries in a season. Galaxies, like everything else, are supposed to be patient. And yet, when we point our most precise instrument at the time when patience should have ruled, what we see instead is hurry. The early universe, as Webb is showing us, was not a slow opening of curtains. It was a sudden flood of light. Among that flood, 6 galaxies in particular caught the world's attention. They were spotted in early Webb data and described in a single short paper that detonated quietly through the field. They were nicknamed, almost reluctantly, the universe breakers. The name was meant as informal shorthand. It became a kind of confession. Each of these galaxies, when their data was measured, showed a stellar mass that did not merely strain the standard model, it tore it. To grow that much stellar material in the time available, gas would have had to convert into stars with an efficiency that real galaxies have never been observed to achieve. Star formation in the universe is normally a wasteful process. Most of the gas that gathers in young galaxies is either blown back out by stellar winds, dispersed by supernova explosions, ionized by ultraviolet light, or simply never collapses into stars at all. A typical galaxy converts only a small percentage of its available gas into stellar mass over its long lifetime. The universe breakers, if their measurements were correct, would have had to convert nearly all of their available gas, almost without loss, in a fraction of the time. There is no mechanism in the standard story that allows for this. There is no known shortcut. There is no known accelerator. And yet, the galaxies were there. Subsequent investigations modified the picture in interesting ways. Some of the six were eventually shown to host bright central black holes that were inflating their apparent stellar masses, since the light from accretion can mimic the light of densely packed stars. This brought a few of them down within the boundaries of the possible, but not all. Several survived even the most rigorous reanalysis. Their brightness could not be entirely explained by black holes. Their compactness could not be entirely explained by measurement error. Their masses could not be entirely scaled away. They remained stubborn, defiant points of light, sitting in an era of cosmic history that should not have produced them. Other surveys then began to find more. Dozens, then hundreds of galaxies in the cosmic dawn appeared more massive, more luminous, more chemically advanced than expected. The universe breakers turned out to be the loudest examples of a quieter, broader rebellion. A pattern was forming. Across many independent telescopes and observation programs, the early universe consistently looked richer, faster, and more crowded than the simulations had been able to anticipate. This is the kind of pattern that keeps cosmologists awake at night. A single anomaly might be a measurement error. Two anomalies might be a coincidence. But a population of anomalies, scattered across surveys, observers, instruments, and methods, is no longer noise. It is signal. The signal that something at the foundation, something deeper than the choice of parameters in a model, is misaligned with reality. Nobody wanted that to be true. The standard cosmological model is one of the most successful frameworks in the history of physics. It correctly predicts the abundance of light elements after the Big Bang, the temperature pattern of the cosmic microwave background, the large-scale clustering of galaxies, the age of the universe to within a few 100 million years, and countless smaller details. To say that something this powerful might be incomplete is to say that the chair you have been sitting on for 50 years has been hovering instead of resting on the ground. You have to look very closely at the chair to convince yourself, but once you see it, you cannot unsee it. Webb has placed cosmology in exactly that position. The chair still works. It still holds. But the legs are no longer resting where everyone thought they were. If the masses of these early galaxies were not enough to unsettle the field, their shapes pushed it further. There is a particular kind of galaxy that lives in the modern universe, and that astronomers find beautiful in a way they rarely admit out loud. These are the disks, the flat, sweeping spiral wheels of stars and dust that resemble fireworks frozen mid-bloom. The Milky Way is one of them. So is Andromeda. So is most of what humanity has historically pointed cameras at. To make a disk like this requires patience. The gas in a galaxy must lose its random motions. It must settle. It must rotate together, in step, around a common center, until the whole structure forms a thin, organized plane. This process takes billions of years in the standard story. It requires gentle conditions, calm gravity, smooth accretion. The early universe, with its frequent mergers and violent gas flows, was supposed to be a hostile environment for disks. The first galaxies should have been chaotic blobs, lumpy and stretched, more like cosmic puddles than cosmic wheels. James Webb did not see puddles. It saw wheels. It saw, in galaxies that existed when the universe was barely a tenth of its current age, the unmistakable structure of disks. Some had clear central concentrations, soft, glowing nuclei surrounded by extended flat envelopes. Some even showed the telltale arches of spiral arms. Surveys revealed that the abundance of disk galaxies in the early universe was not a small fraction. It was a substantial portion of all observed galaxies. Some studies suggested that in certain cosmic eras, more than half of large galaxies already wore disk shapes. This was not what anyone had been ready to find. To produce so many disks so early, gas would have had to settle far faster than expected. Mergers would have had to be far less destructive. Dark matter halos, the invisible scaffolding around galaxies, would have had to mature far quicker than predicted. Each of these adjustments has consequences that ripple outward. If gas settles faster, then star formation timescales must shift. If mergers are less destructive, then the way galaxies build up over time must be reconsidered. If dark matter halos mature earlier, then the first half-billion years of the universe must have been gravitationally busy in ways the simulations never predicted. Together, these changes amount to something larger than fine-tuning. They suggest that the cosmic dawn was not a slow stirring of matter, but an aggressive self-organization. The universe, at the time it should have been still finding its feet, was already learning to spin. There is a strange poetry in this image. The young cosmos, full of energy and gas, did not stagger forward. It pirouetted. It found rotation almost immediately. Whatever instinct gravity carries inside it, it expressed that instinct early. And that early expression, more than anything, is what threatens the textbooks. The textbooks were built around the idea that complexity takes time. Webb is showing us a universe in which complexity may simply be the default. Order arrived along with light. And the consequences of that one observation, the consequences of disks where there should have been chaos, are still spreading through the field as new data arrives every month. This is where the real puzzle deepens, and it does so along an axis that may surprise you. It is not simply that early galaxies were too big or too organized. It is that the entire timing of the universe seems, when measured carefully, to no longer agree with itself. There are two ways to measure how fast the universe is expanding. One method uses the oldest light in the cosmos, the gentle microwave glow released about 380,000 years after the Big Bang. By analyzing the tiny fluctuations in that ancient signal, scientists can extrapolate forward and predict how fast space should be stretching today. The other method works in the present. It measures the distances to nearby galaxies using bright stars that pulse with predictable rhythms and supernovae that explode with a known peak brightness. By comparing how far away these objects are with how quickly they are moving away from us, scientists can directly measure the current rate of expansion. Both methods are extraordinarily precise. Both methods have been refined for decades, and both methods stubbornly disagree. The early universe says the cosmos should be expanding at one rate. The local universe insists it is expanding at a slightly faster rate. The difference is small in absolute terms, but in the careful arithmetic of cosmology, it is a chasm. The universe cannot have two expansion rates simultaneously. Either one of the measurements is wrong, or something is happening between the early universe and now that the standard model does not include. For years, scientists hoped that improving the instruments would close the gap. They hoped that more precise data would reveal which side had been making a small error. James Webb, with its extraordinary sensitivity, was supposed to be the deciding instrument. Instead, the telescope sharpened both measurements without resolving the disagreement. The tension did not melt away. It held. In some ways, it grew. This problem, called the Hubble tension, is now one of the most important puzzles in modern physics. It is no longer treated as a curiosity. It is treated as a clue that something fundamental is missing from our understanding of how the universe evolves between its earliest moments and its present state. Several explanations have been proposed. Some involve a hypothetical phase called early dark energy. in which a brief surge of unknown energy slightly accelerated the cosmos in its first few 100,000 years before fading away. Others suggest that the properties of dark matter might shift subtly over cosmic time, changing how gravity organizes structure. Others propose that there may be extra particles in the early universe, faintly interacting, contributing to a slightly different expansion history than we currently model. None of these ideas is comfortable. Each requires inventing or modifying a piece of physics that has never been directly observed. But the alternative, which is to insist that all measurements are wrong despite their agreement on every other front, is even more uncomfortable. So the field has settled into a careful, watchful stance. Cosmology is waiting to see what gives way first. Meanwhile, Webb's discoveries about the early universe, the heavy galaxies, the disks, the chemistry that should not be there yet, all push gently in the same direction. They suggest that the early universe was not the obedient cradle the Standard Model imagined. It was already deviating, already running by rules we have not fully described. And as we step deeper into Webb's observations, that deviation only grows louder. There is a kind of measurement that all of cosmology relies on without often saying so out loud. It is the cosmic distance ladder. To know how fast the universe is expanding, you must know how far away things are. To know how far away things are, you need a chain of trustworthy markers, each one helping you reach a little farther than the last. The bottom rung uses parallax, the slight shift in the apparent position of nearby stars as Earth orbits the Sun. The next rung uses a special kind of star called a Cepheid variable, which pulses in brightness at a rate that reveals how luminous it truly is. By comparing that true luminosity to how dim it looks from Earth, astronomers can calculate distance with surprising accuracy. Higher rungs use exploding stars called type Ia supernovae, which detonate with such consistent brightness that they can be seen from the far side of the observable universe. Each rung depends on the rung below it. If the lower steps wobble, every higher step wobbles too. James Webb, in addition to peering into deep time, has been carefully studying these distance markers. Its infrared eyes can see Cepheid variables in galaxies where Hubble could only guess at them, surrounded by other stars that, in older images, blended together into a single confused glow. With Webb, those crowded fields can be resolved into individual stars, each one cleanly separated from its neighbors. The result is the most precise distance measurements ever made for these objects. And the data, when analyzed, has done something subtle and unsettling. It has reaffirmed, with even greater confidence, that the local expansion rate of the universe is what local methods say it is. The Hubble tension cannot be blamed on confusion in the Cepheid measurements. The disagreement between early and late universe measurements is not an artifact. It is a real feature. Whatever is causing it, it lives in physics, not in instrumentation. Some teams, however, have begun finding hints of even subtler issues. They are looking at whether Cepheid variables in galaxies of different chemical compositions might shine slightly differently than Cepheids in our own neighborhood. They are looking at whether type Ia supernovae behave the same in young galaxies as in old galaxies, or whether their brightness depends in tiny ways on their environments. None of these effects, if real, are large. But cosmology is a field where small effects can hide large stories. A 1% shift in the calibration of distance markers could erase or amplify the Hubble tension. A 1% shift in the assumed brightness of supernovae could ripple through every estimate of how the universe has been expanding for the last several billion years. So far, every careful test has only deepened the puzzle. The standard candles flicker and we cannot tell whether the flicker is in the candles or in the universe itself. This kind of uncertainty has a cumulative effect. It does not just affect the Hubble constant. It affects every quantity that depends on knowing how time and distance unfold across the cosmos. The age of the universe, the size of the observable universe, the growth rate of cosmic structure, the amount of dark energy, the behavior of dark matter. They all rest, ultimately, on the same chain of measurements. If the chain has even a single faint kink, the entire picture must be re-examined. Webb, by sharpening every rung at once, is forcing cosmology into one of the most delicate self-checks it has ever undertaken. It is not breaking the ladder. It is showing us that some of the rungs, on closer inspection, are not quite where we believed they were. And among the things that depend on this ladder, perhaps the most haunting is the apparent age of certain galaxies. Because Webb has now shown us a galaxy whose stars, by some measurements, appear to be older than the universe is supposed to be. There are not many sentences a scientist can say that will silence a room. One of them is, "This object is older than the universe." It is the kind of statement that, on its face, simply cannot be true. The universe contains everything inside it. Nothing in it can predate it. To suggest otherwise is to point at a contradiction, an arithmetic that has gone wrong somewhere along the way. And yet, as Webb's data has been analyzed, certain galaxies have produced exactly that contradiction. The story usually unfolds in 3 quiet steps. First, the galaxy's distance is measured, placing it at some early moment in cosmic history, perhaps several hundred million years after the Big Bang. Second, the galaxy's stellar populations are studied, looking at the colors and chemistry of its light. Stars of different ages produce different signatures. Old stars are cooler, redder, more chemically processed. Young stars are hotter, bluer, simpler. Third, the model converts those signatures into an estimated age. The age tells how long the stars in the galaxy have been shining. This number, in some Webb observations, has come back stubbornly large. Larger than the time available between the Big Bang and the moment the galaxy was observed. Sometimes by hundreds of millions of years. Sometimes by what appears to be a full billion. There are, of course, ways to soften this. The age models depend on assumptions about how stars behave in the early universe. If those assumptions are slightly off, the apparent ages can shift. Stars in the cosmic dawn formed from gas with very few heavy elements. Their surfaces, atmospheres, and life cycles may have been different from the stars we know today. If we underestimate how quickly such stars age, or how their colors evolve, we may overestimate how long they have been shining. Some teams have argued precisely this. They suggest that the apparent old ages of certain early galaxies are likely a sign that our models of primitive stars need refinement. Others, however, have not been satisfied with that explanation. They have rerun the analyses with multiple models, used independent methods, and adjusted assumptions in every reasonable way. The contradiction has stubbornly remained. A small but persistent population of distant galaxies appears, by the careful logic of stellar age dating, to contain stellar populations that are simply too mature for the cosmic time available. This is an alarm bell, but it is a polite one. It does not mean these galaxies actually predate the universe. The most likely interpretation is that something in our framework is slightly miscalibrated. The age of the universe might be a touch larger than the standard model suggests. The early stars may form and process material on a faster timeline than expected. The standard candles that anchor distance measurements may be subtly biased. Any one of these small adjustments could resolve the apparent paradox. But each of those small adjustments brings consequences elsewhere. Increase the age of the universe, and the Hubble tension shifts. Speed up early star formation, and the universe breakers become slightly less impossible, but more puzzling in other ways. Adjust the distance ladder, and dark energy estimates change. Cosmology is a deeply interconnected web. You cannot pull one thread without sending tremors across the others. The galaxies that appear too old are not simply curiosities. They are tugging at the same thread that the Hubble tension is pulling, and that thread leads to the same place. Something in the timeline of the universe is not what we have been assuming. The universe may be older than we have written down. The early universe may have been busier than we have allowed for. Time itself, in the way cosmology measures it, may have an extra quiet chapter that we have not yet fully read. And as Webb continues to look further into that early era, it has set new records that emphasize the point. One of those records came from a small, faint object whose distance turned out to be greater than any previously measured galaxy. The galaxy, when finally confirmed in its identification, was given a long technical name that astronomers shortened into something easier to carry in conversation. It became known by its position in a survey called JIDES, with a number attached to mark its place in the catalog. The light from it had been traveling for nearly 13.5 billion years, leaving the universe shortly after the cosmic dawn truly began. To see it was to look at the universe when it was less than 300 million years old, which is about 2% of its current age. By every standard expectation, a galaxy this far back should have been faint, small, primitive, the rough outline of something that had not yet figured out how to be a galaxy. Webb confirmed otherwise. The object was not faint enough. It was not small enough. It was not primitive enough. It was already, in many ways, recognizable. Its spectrum revealed clear signs of oxygen, an element that requires generations of stars to be created and dispersed. Its size, although modest by modern standards, was substantial for its era, spanning more than 1,000 light-years across. Its stellar mass implied that hundreds of millions of suns' worth of stars had already formed within it. To produce all of this in a few 100 million years would require a level of cosmic efficiency that current models cannot easily provide. There are theories, of course. Some suggest that the first generation of stars exploded in unusually massive supernovae, scattering their elements quickly through the surrounding medium. Others propose that early galaxies were embedded in unusually dense regions of dark matter that allowed gas to gather and form stars far faster than typical conditions allow. Still others wonder whether the very first phase of cosmic history simply ran on a different metabolism, with light and matter exchanging energy in ways that allowed structure to coalesce more quickly than the equations now imagine. None of these ideas are comfortable. Each requires extending or modifying some part of the standard story. And yet, the galaxy is real. Its distance has been confirmed by spectroscopic measurements, the most reliable form of cosmic distance check. Its chemistry has been verified by examining the wavelengths of its light. Its mass has been estimated from multiple methods. The result holds. A galaxy this developed, this chemically rich, this organized, existed in an era that our models do not allow it to exist in. Setting a new record for the most distant galaxy ever confirmed is the kind of milestone that makes a headline for a few days and then fades. But for the astronomers analyzing the data, the milestone is less important than what it implies. Each new record is showing the same pattern. The early universe is more advanced than our models permit. Each new measurement does not push the boundary of impossibility back. It deepens the puzzle in place. There is something about the cosmic dawn that we are still not seeing. Something that allowed the first galaxies to assemble themselves with surprising speed. Something that allowed elements to spread through gas with unexpected reach. Something that allowed light to organize itself into structure long before our equations expected light to be doing anything that interesting. The deeper Webb looks, the louder this hidden chapter of cosmic history becomes. And among the discoveries it has already produced, perhaps none echoes that hidden chapter more sharply than what it has revealed about black holes, the most extreme objects in the universe, appearing in numbers and sizes that should not have been possible. A black hole is a place where the rules of ordinary physics give up. At its center, density approaches infinity. Around its boundary, time itself slows. Light, which travels through every other corner of the universe with effortless certainty, encounters here a surface from which it can no longer escape. There are small black holes, the kind formed when massive stars collapse. There are intermediate black holes, the rare middle children of the cosmic family. And there are supermassive black holes, the kind that lurk at the centers of nearly every large galaxy, weighing millions to billions of times the mass of the Sun. The Milky Way has one, and so does Andromeda, and so does almost every galactic system worth naming. These supermassive black holes are not optional accessories to galaxies. They appear to grow alongside their hosts, exchanging mass and influence with their surrounding stars in ways that astronomers are only beginning to understand. The traditional story of how they came to be required time. A black hole begins small, the size of a collapsed star, perhaps a few times the mass of the Sun. It then has to grow. It can grow by swallowing gas, by merging with other black holes, by gradually accumulating material from its environment. There is a maximum rate at which this growth can happen, set by the physics of how matter falling toward a black hole heats up and pushes outward against further infall. This limit, named after the British physicist Arthur Eddington, has long served as a kind of speed governor for cosmic monsters. Even at its maximum, growth from a stellar seed to a supermassive billion solar mass giant takes nearly 1 billion years of continuous, undisturbed feeding. The early universe, by contrast, is barely that old at the eras Webb has been examining. And yet, when Webb looked, supermassive black holes were already there. Some of them had masses approaching 1 billion suns. Some sat at the centers of galaxies less than 700 million years after the Big Bang. There is no clean way to explain this with the traditional story. The seed had to be larger than a stellar collapse could produce. The growth rate had to be more sustained than realistic feeding could allow. Or the universe itself had to provide some shortcut that current physics has not described. Several proposals have emerged, each more dramatic than the last. One suggests direct collapse, in which giant clouds of pristine hydrogen, in the very first generation of cosmic structure, skipped the stellar stage entirely and collapsed directly into black holes weighing tens of thousands of solar masses from the start. Such seeds would have a head start large enough to grow into supermassive monsters in the time available. Another proposal suggests that early black holes broke the Eddington limit through brief, exotic episodes called super-Eddington accretion, in which gas is funneled inward faster than radiation can push it back out. Yet another, perhaps the strangest of all, returns to a long-dormant idea about primordial black holes formed in the first instance after the Big Bang itself, before any star had ever shone. If such relics exist, they could provide the seeds Webb is now seeing in their grown-up form. None of these ideas is yet proven. Each invites further questions. but the data has made avoiding the question impossible. The cosmos somehow built supermassive black holes faster than our equations say it should. Whatever mechanism allowed this, it operated in the very first chapters of cosmic history. It was active when the first galaxies were still finding their shapes, and in some cases, it appears to have been active before those galaxies had finished forming. There are objects in Webb's data that suggest the central black hole and the galaxy around it grew up together, but with the black hole carrying an outsized share of the partnership. This rebalancing of the ancient cosmic relationship has consequences that astronomers are still tracing, and one of the most striking signs of it appears in a curious population of small, intensely red points scattered across Webb's deepest images. When the first deep field surveys were processed, astronomers noticed an unusual class of objects appearing again and again. They were tiny, often appearing as single-point sources rather than extended galaxies. They were intensely red, suggesting that their light had either been stretched by enormous distance or filtered through significant amounts of dust, or both. They were surprisingly bright for their size, and they were everywhere. They became known, almost casually at first, as the little red dots. The casual name belied their importance. As more spectroscopic data was collected, the dots began to reveal themselves as some of the most extreme objects in the early universe. Many of them appeared to host supermassive black holes far heavier than any reasonable stellar mass would suggest for the surrounding galaxy. In some cases, the central black hole appeared to weigh nearly as much as the entire visible stellar content of its host galaxy. In others, it appeared to weigh more. This is not how things are supposed to work. In the modern universe, supermassive black holes typically weigh about 0.1% of their galaxy's total stellar mass. The relationship is so consistent that it is one of the cleaner correlations in extragalactic astronomy. It hints at a deep coupling between black hole growth and galactic growth, a slow co-evolution over billions of years. The little red dots break this relationship. They suggest that in the early universe, the central black hole was not a small fraction of its galaxy. It was the dominant feature. The galaxy, in some sense, had not yet grown to match its centerpiece. This inversion is more than a curiosity. It changes the very order of cosmic construction. In the old story, galaxies formed first, gathering gas and stars, and the central black hole grew slowly along with them. In the picture suggested by the little red dots, the black hole came first, or grew faster than its galaxy could keep up with, and then the galaxy assembled around or below it. The implications stretch through astronomy. If black holes lead the dance, then their gravitational and radiative influence helped shape the way galaxies formed in the first place. They set the stage, rather than playing a supporting role. They are not afterthoughts to galactic evolution. They are perhaps the protagonists of the cosmic dawn. Several explanations have been offered for what the little red dots actually are. Some teams interpret them as compact, dust-shrouded galaxies hosting feeding black holes whose accretion light dominates over starlight. Others suggest that the redness comes mostly from the light of small, highly evolved stars combined with extreme distance, and that the central black hole signature is more subtle than first interpreted. Still others believe that what we are seeing is a previously undiscovered phase of cosmic evolution, in which black holes grew far ahead of their galaxies for a brief but crucial period, leaving behind a population that simply has no analog in the modern universe. As the data accumulates, these interpretations are slowly being narrowed down, but what is already clear is that the little red dots are not a fluke. They appear in large numbers across many fields, in many surveys, with consistent properties. Whatever they were common in the early universe, and their existence supports the larger picture that Webb has been quietly building. The cosmic dawn produced black holes faster, in greater numbers, and at higher relative masses than anyone had been ready to admit. And those black holes, in turn, may have lit up the cosmos in ways that helped drive its earliest transformations. The most spectacular form of black hole illumination is the quasar, and quasars in the early universe present yet another puzzle that Webb has not so much solved as deepened. A quasar is a supermassive black hole caught in the act of feeding. As gas spirals inward toward the event horizon, it heats up under enormous gravitational pressure, releasing radiation across nearly every wavelength of light. The result is one of the most luminous objects in the cosmos, brighter than entire galaxies, capable of being seen across distances so vast that they reveal the universe as it was when it was a small fraction of its current age. Quasars are, in a sense, cosmic lighthouses. They illuminate the gas around them, giving astronomers a way to study the chemistry and structure of the early cosmos. But to make a quasar, you need a supermassive black hole. And to make a supermassive black hole in the early universe, you encounter the same growth problem we have been circling. The deeper Webb has looked, the more quasars it has identified at distances that strain the standard model. Some quasars are now confirmed to have existed less than 700 million years after the Big Bang, and a few may exist even earlier. Each one, by its very brightness, implies a fully grown supermassive black hole sitting at its core. Each one implies, therefore, that the universe was somehow able to produce such a monster in less time than the equations should allow. If you accept the standard Eddington limit, then the seeds of these quasars must have started life already large. The idea of direct collapse mentioned earlier becomes not just a possibility, but almost a necessity. Without it, the math does not work. With it, the math works only barely. Even with direct collapse seeds of tens of thousands of solar masses, the growth must be sustained, uninterrupted, and remarkably efficient to reach billion solar mass scales by the eras Webb is observing. There is, in addition, the chemistry that surrounds these early quasars. By examining the absorption lines that appear in quasar light as it travels through nearby gas, astronomers can map what elements are present in the quasar's environment. The result is, again, surprising. The gas around early quasars often contains substantial amounts of metals, the astronomical term for any element heavier than helium: iron, magnesium, oxygen, carbon. Each of these elements has to be forged inside stars and then dispersed by stellar deaths. The presence of significant amounts of metals around quasars in the cosmic dawn implies that not only had supermassive black holes already grown, but also that earlier generations of stars had already lived and died nearby, seeding the local gas with the products of their nuclear fires. The first stars must have been numerous and massive enough to produce these metals. Their explosions must have been powerful enough to scatter them widely. And all of this must have happened in a window of time so narrow that it leaves cosmologists unsettled. Each part of this story is plausible in isolation. Strung together, with the timeline as tightly compressed as Webb is showing, they form a chain whose every link strains under the load. The simplest interpretation is that the early universe was simply more capable than we have allowed ourselves to imagine. It grew fast. It enriched itself fast. It built monsters fast. The cosmos, in its infancy, was not crawling. It was sprinting. And as Webb continues to map this sprint, the patterns it reveals are forcing cosmologists to consider whether something deeper than parameter tuning is at work. There may be a chapter of physics, hidden in the first few 100 million years of cosmic history, that we have not yet learned how to read. If you have come this far, you have already followed light across 13 billion years and back. You have stood beside galaxies that should not exist and black holes that grew too fast. There is more to come, much more. But for a moment, let the silence return. Let your shoulders soften. The cosmos is not going anywhere. It has been waiting longer than you can imagine for you to listen to it. And it does not mind waiting a little longer while you breathe. If this journey has begun to settle something in you, if it has slowed your thoughts even a little, consider quietly subscribing to the channel so that the next of these long, patient nights can find you when it arrives. There is no urgency to it. The stars are not in a hurry. But if you choose to come back, this small place on the internet will be here, drifting steadily through whatever comes next, ready to keep walking with you across the dark. There is a class of cosmic puzzle that does not announce itself loudly. It does not arrive as an impossible galaxy or a record-breaking distance. It arrives as an absence, a quiet emptiness where the equations promised a crowd. For decades, the standard story of how galaxies form has predicted a particular kind of cosmic neighborhood. Around every large galaxy, like the Milky Way, there should be a swarm of much smaller companions. These tiny galaxies, called dwarfs, are supposed to be the leftovers and forerunners of cosmic structure. Their existence is not optional within the standard model. Cold dark matter, the invisible scaffolding that builds the gravitational web of the universe, was supposed to fragment into countless small clumps. Each clump should attract enough gas to form a small galaxy. Each large galaxy should therefore be surrounded by hundreds, perhaps thousands, of these small companions. The Milky Way, by this prediction, should have something like 500 to 1,000 satellite galaxies. We have found a few dozen. Andromeda, our nearest large neighbor, should also be wreathed in dwarf companions. Again, only a small fraction of the expected number have ever been observed. This shortfall has been called the missing satellites problem, and it has haunted cosmology for decades. Some scientists have argued that the missing dwarfs simply have not been found yet. Many of them might be too faint to detect. Some might have lost most of their gas to ultraviolet radiation in the early universe and never managed to form many stars. They could still be out there, dark or nearly dark, ghostly clumps of dark matter drifting around larger galaxies, waiting for instruments sensitive enough to find them. James Webb was supposed to be one of those instruments. With its remarkable infrared sensitivity, it should have been able to detect even the faintest stellar populations in nearby dark matter halos. As the surveys came in, the news was, in a sense, mixed. Webb did find new dwarf galaxies, both nearby and at intermediate distances. It increased the count modestly. But it did not produce the flood of new objects the simulations had hoped for. The missing dwarfs, by and large, remained missing. This absence is meaningful. It is one of the strongest pieces of empirical evidence that the standard cold dark matter picture, while broadly successful, may be missing something at small scales. There are several proposed alternatives. One, called warm dark matter, suggests that dark matter particles move slightly faster than the cold model assumes. This faster motion smooths out the formation of small structures, naturally reducing the number of dwarf galaxies expected. Another, called fuzzy dark matter, proposes that dark matter is made of extraordinarily light particles whose quantum wavelengths span enormous distances. On small scales, these wavelengths suppress the formation of tiny halos. Self-interacting dark matter, yet another proposal, allows dark matter particles to occasionally bump into each other, gently rearranging their distribution in ways that might also reduce small-scale structure. None of these alternatives is yet confirmed. None has been definitively ruled out. The missing satellite problem, in this sense, is a mystery in waiting. It is also a reminder that some of the most important cosmic clues lie not in what is found, but in what is not. The universe whispers as much by its silences as by its speeches. Webb is sharpening that listening, even when the answer remains incomplete. And the missing dwarfs are not the only quiet anomaly. Other patterns are beginning to emerge in the data, patterns that suggest that the universe, at its largest scales, may not be quite as uniform as we have always assumed. If you ask a cosmologist what the universe looks like at the largest scales, you will hear a phrase that gets repeated like a prayer. The universe, they will say, is isotropic and homogeneous. Isotropic means it looks the same in every direction. Homogeneous means it has the same average density everywhere when you zoom out far enough. These two assumptions are the backbone of modern cosmology. They are not mere conveniences. They are written into the equations that describe how space expands. They are why we treat the cosmos as a single, well-defined object with a single, well-defined history. Without them, the entire mathematical framework would have to be reconstructed from a different foundation. For most of the last century, observational data has supported these assumptions, at least to a useful approximation. The cosmic microwave background, the most ancient light we can measure, looks remarkably uniform across the sky. Galaxy distributions, when averaged over enormous volumes, appear evenly spread. Whatever asymmetries exist seem small enough to be ignored. But over the past decade, and especially with Webb's deeper data, faint signs of something else have begun to surface. Several teams have noticed that galaxies, when classified by their direction of rotation, do not appear to be perfectly balanced. As we look out at large samples of galaxies, we should expect equal numbers spinning clockwise and counterclockwise, as seen from our perspective. The cosmos, by every assumption of isotropy, should not care which way galaxies spin. Yet, in some surveys, including those built on data sharpened by Webb, a small but persistent excess has been seen in one rotational direction over the other. The asymmetry is small, just a few percent, but it is statistically stubborn. It has been measured by multiple groups, with different methods, in different parts of the sky. Each time, the bias persists. There are several ways to interpret this. One possibility is that the asymmetry is an artifact, a subtle bias introduced by the way galaxies are imaged, classified, or measured. Cosmologists are very cautious about this possibility, since human and instrumental biases are notoriously difficult to eliminate. Another possibility is that the asymmetry reflects a real, large-scale imbalance in the universe. Perhaps the cosmos has a slight preferred orientation, a faint cosmic axis along which structure prefers to rotate or align. If this turned out to be real, it would shake the foundations of cosmology. The standard model would have to make room for some kind of broken symmetry, some explanation for why the universe leans, however slightly, in one direction. There are even more exotic possibilities. Some theorists have proposed that the universe itself might be slowly rotating, on scales so vast that the rotation is imperceptible from within our local cosmic neighborhood, but detectable as a tiny bias in galaxy spins. Others propose that the cosmic axis we are detecting is a remnant of the very first instance after the Big Bang, when the universe might have undergone subtle anisotropic phases that have left fossil traces in the structure that followed. None of these ideas can yet be confirmed. The data, while suggestive, is not yet decisive. But the consistency of the asymmetry across surveys and across methods is making cosmologists uncomfortable in a productive way. It is forcing the field to question one of its oldest assumptions. The universe, taken as a whole, may not be perfectly even. It may carry, woven into its largest patterns, a quiet preference, a direction, a faint cosmic lean that we have not yet learned to interpret. And as Webb continues to gather data on the distribution and orientation of galaxies, this lean is one of the puzzles its observations are likely to either confirm or dispel. Whichever way the answer falls, the question itself has already changed the conversation. There is another puzzle, related but distinct, that Webb has helped sharpen. It concerns not the orientation of galaxies, but the way they are connected to each other across enormous distances. The universe, on the largest scales, is not random. Galaxies are not scattered like grains of sand. They are arranged into vast, branching filaments. These filaments connect to each other at dense crossroads called nodes, where galaxy clusters live. Between the filaments lie immense, nearly empty regions called voids. Together, this pattern is known as the cosmic web. The cosmic web is built by gravity over billions of years. Tiny initial fluctuations in the early universe grow under their own gravitational pull, attracting more matter, becoming filaments and clusters and voids. The standard model predicts that this assembly is gradual. The web should appear blurred and weak in the early universe and sharpen over cosmic time as gravity has more opportunity to do its work. By the modern era, the web should be fully developed, glittering with structure across hundreds of millions of light years. James Webb, when it began studying the distribution of distant galaxies, has revealed something subtly unsettling. The cosmic web appears to have begun assembling earlier and more aggressively than expected. Filaments connecting galaxies stretch across substantial distances even in the early universe, when the standard model expects only the faintest hints of large-scale structure. In some Webb observations, chains of galaxies appear to be aligning along filamentary patterns that already resemble the modern cosmic web in miniature. The implications of this are not as dramatic as the impossible galaxies or the early black holes, but they share the same flavor. The early universe was already organizing itself at scales the simulations did not expect. Gravity, somehow, was working faster, or the initial conditions of the universe were not quite as smooth as the standard model assumes, or both. To accelerate cosmic web assembly in the way Webb seems to suggest, the early universe would have needed slightly stronger initial density fluctuations, or slightly different dark matter dynamics, or a slightly older starting point. Each of these adjustments connects to the other puzzles already discussed. None of them is independent. The Hubble tension, the early massive galaxies, the early supermassive black holes, the apparent old ages of certain stellar populations, the early disk galaxies, and now the early cosmic web. They all push, however softly, in the same direction. They all suggest that the universe began doing things sooner, faster, and with more vigor than our equations have allowed. Cosmologists have a phrase for situations like this. They call it converging tension. When several independent puzzles begin to align in the same direction, the field begins to suspect that they share a single underlying cause. They are not separate mysteries. They are different facets of the same hidden truth. If that truth turns out to be a small adjustment in the age of the universe, much of the tension dissolves naturally. If it turns out to be a more fundamental revision of dark matter, of inflation, of gravity itself, then cosmology stands at the threshold of a new chapter. Either way, the cosmic web that Webb is mapping is not just a beautiful pattern, It is one more piece of evidence that the early universe wove itself together more quickly than we have written down. There is one place in the sky where the dance of dark matter is not subtle. It is dramatic, almost theatrical, frozen in the aftermath of a cosmic collision. It is called the bullet cluster. Around 3 billion years ago, two galaxy clusters smashed into each other at speeds greater than anything most of us could meaningfully picture. Each cluster carried hundreds of galaxies, vast clouds of hot gas, and enormous halos of dark matter. As they passed through each other, the visible matter, primarily the hot gas, slowed down due to electromagnetic interactions, like fluids encountering resistance. The dark matter, having no such friction, kept moving. The result is a cluster system in which the hot gas, traceable through X-ray emission, sits in the middle, slightly displaced from the bulk of the matter, while the gravitational pull, traceable through the way the cluster bends light from background galaxies, is centered elsewhere, at the locations of the galaxies and their associated dark matter halos. The visible matter and the gravitational center are no longer in the same place. This separation is one of the cleanest, most striking pieces of evidence ever found for the existence of dark matter. It is hard to explain without invoking some form of unseen mass. Modified gravity theories, which try to explain galactic dynamics without dark matter, struggle particularly hard to reproduce what the bullet cluster shows. James Webb has not replaced the X-ray data, but it has added a new layer of detail. By studying the precise distortions of background galaxy light caused by the bullet cluster's gravity, and by mapping faint galaxies inside and behind the cluster with new clarity, Webb has produced refined dark matter maps with finer resolution than anything before. The new maps confirm the basic picture. The dark matter and the visible matter are clearly separated, but they also reveal subtleties. The dark matter halos appear to have small substructures, faint variations, hints of clumping or smoothing that previous instruments could not resolve. These details are now being analyzed to test the various dark matter models. Cold dark matter predicts certain kinds of substructure. Warm and self-interacting dark matter predict different patterns. The bullet cluster, with Webb's added detail, is becoming a laboratory in which some of these models can be more carefully tested. So far, the data is suggestive, but not definitive. Some teams have noticed signs that may favor models in which dark matter particles have weak self-interactions. Others are not yet convinced. But the very fact that Webb can resolve such fine differences in the dark matter distribution of a distant cluster is a remarkable demonstration of how far observational cosmology has come. Whatever dark matter turns out to be, the bullet cluster will likely play a starring role in the final answer. It is the rare astronomical object whose observation alone narrows the field of possibilities. And as Webb continues to study it and similar systems, the noose around the true nature of dark matter quietly tightens. We may not know yet what dark matter is, but we are learning in increasingly precise detail what it is not. Beyond galaxies and clusters and dark matter, Webb has been forced to revisit something even more basic about the early universe: its chemistry. The early cosmos was supposed to be chemically simple. According to the standard story, the Big Bang produced almost exclusively the lightest elements: hydrogen, helium, and a tiny trace of lithium. Everything else, every other element on every periodic table that has ever been printed, had to be made later. Inside stars, through fusion, through the violent deaths of stars in supernovae and other catastrophes. Generation after generation of stars had to live and die before the universe could accumulate meaningful amounts of carbon, oxygen, iron, silicon, and the rest. The early universe, by this logic, should have been chemically pristine. The first generations of stars should have formed from hydrogen and helium alone, free of the heavier elements that flavor every modern star, including our own Sun. This kind of pristine star is called a population 3 star, and finding one has been one of the great quiet quests of modern astronomy. James Webb did not find a chemically pristine early universe. Even at its deepest, when it looked at galaxies just a few 100 million years after the Big Bang, it found evidence of carbon, oxygen, neon, and other heavier elements, sometimes in surprising abundances, sometimes only modestly above the expected pristine baseline, but always more than zero. To produce these elements, earlier generations of stars must have already lived, died, and scattered their products into the surrounding gas. And those stars must have done so in a window of time so short that it leaves cosmologists with very little room for the slow chemical evolution our textbooks describe. There are several ways to interpret this. One is that the very first stars were enormous, far larger than the typical stars of today. A massive star burns brightly and dies quickly. If the first stars were truly gigantic, they could have lived for only a few million years before exploding as colossal supernovae, scattering their fused elements into the surrounding gas. A few million years is a fast turnaround on cosmic timescales. It might just allow heavy elements to be produced in time for the galaxies Webb is now observing. The challenge, however, is producing enough such stars to do the job. Pristine gas is reluctant to fragment into small clumps without heavier elements to help it cool. The first stars, therefore, tended to be very massive, but also relatively rare. To enrich the early universe to the levels Webb is observing, either many more such stars formed than we expected, or each star scattered its elements far more widely, or both. Another possibility is that the early universe contained denser regions, primordial overdensities, where rapid star formation could occur in concentrated zones. The chemical enrichment in these zones could have spread quickly through nearby gas, producing local pockets of relatively rich chemistry, while other parts of the cosmos remained more pristine. Webb's data, when carefully analyzed, does suggest some patchiness in early enrichment, with some galaxies showing more advanced chemistry than others at the same cosmic age. Still, another possibility is more provocative. Some scientists have begun asking whether the very first phase of cosmic structure might have been different from anything in the standard story. Perhaps the chemistry that Webb is finding requires not just unusually massive first stars, but processes we have not yet identified. There are theoretical proposals involving exotic decays of dark matter, or hypothetical particles that briefly enhanced star formation in the cosmic dawn, or even more speculative ideas about the connections between dark matter and ordinary matter in the first instance after the Big Bang. None of these proposals are accepted as the leading explanation, but they are no longer dismissed automatically. The chemistry problem, like several others Webb has revealed, has reached a level of strangeness where unconventional ideas at least deserve a hearing. Yet, despite this evidence of early chemistry, one of the strangest absences in Webb's data remains the very stars that should have made it possible. Population 3 stars, the ghosts of the cosmic dawn, have not been definitively observed. There have been candidates. There have been hopeful spectra. There have been small chemical signatures in distant galaxies that hint at populations of pristine stars buried somewhere in the data. But no single, unambiguous population 3 star has yet been confirmed in a way that the field as a whole is willing to accept. This is frustrating. Population 3 stars are central to the cosmic story. They are the bridge between the chemical simplicity of the Big Bang and the chemical richness of every later star. Without them, the universe could not have produced its current chemistry. Without them, planets could not have formed. Without them, life as we know it could never have begun. They are essential, foundational, and yet, so far, invisible. There are several reasons they are hard to find. Population 3 stars, by being made of pristine gas, would have produced very specific spectral signatures, dominated by ionized hydrogen and helium, with almost no metal lines. To detect these signatures clearly, an instrument must observe a region rich enough in these stars to overcome the contaminating light of nearby, later generation stars and gas. Such regions are rare, small, and easily diluted by surrounding light. Even Webb, with its remarkable sensitivity, has so far been unable to isolate them with full confidence. There are several leading interpretations of this scarcity. One is simply that population 3 stars formed for a very brief time in the cosmic history, and that subsequent generations quickly took over, drowning out their signature. The pristine gas necessary to make them would have been chemically polluted by the explosions of the first generation, ending their era almost as soon as it began. Another interpretation is that population 3 stars were not as universally massive as we have assumed. Perhaps a portion of them formed at lower masses, lived longer, and persisted into the era of more enriched galaxies, where their signal would now be hopelessly mixed with later populations. A third interpretation, more troubling, suggests that the standard picture of population 3 formation may itself need revision. If pristine gas could fragment more easily than current models suggest, then the first stars might have formed at smaller masses, with longer lifetimes, in larger numbers. Their signal would be different from what we have been searching for. We may have been looking for ghosts shaped like giants when, in fact, they were shaped like ordinary stars all along. Webb's continued surveys are sharpening these questions. Each new spectrum, each new deep field, contributes a piece to the puzzle. The answer, when it eventually comes, will likely combine elements of all these interpretations. But for now, the absence of clean population 3 observations is one of the clearest indicators that something in the bridge between the Big Bang and the modern stellar zoo remains unfinished business. The first stars did exist. They had to. Their signatures, however, are subtle, scattered, and stubbornly resistant to being pinned down. And in a curious way, this absence echoes the larger pattern that Webb's observations have produced. The early universe, when carefully examined, refuses to behave the way our simplest models predicted. Some things appear too soon. Other things, expected to leave loud traces, leave only whispers. Whatever the early cosmos was, it was both more eager and more elusive than we imagined. One of the substances that should not exist in significant amounts in the early universe is the very thing that, on Earth, gathers on bookshelves and ledges: dust. Cosmic dust is a misleading name, because the dust in space is not the kind that drifts through old houses. It is made of microscopic grains of silicates, carbon, and other compounds, scattered through the gas between stars. Dust grains are formed primarily in the late stages of stellar evolution. Stars near the end of their lives shed their outer layers, and as that material cools and condenses, dust grains form. Supernovae also produce dust, sometimes in surprising amounts. But all of these processes require stars to have formed, lived, and ended. Dust, like heavier elements, is supposed to take time. The early universe should be nearly dust-free. Webb did not find a dust-free early universe. It found galaxies in the cosmic dawn, only a few 100 million years after the Big Bang, that already contained substantial amounts of dust. Their light was reddened in characteristic ways. Their infrared signatures revealed warm dust emission that should have taken billions of years to develop. Some early galaxies showed dust contents comparable to what we see in modest galaxies of today, despite being observed at an era when, by every standard model, they should have been nearly transparent. To produce this much dust so early, the universe must have run its dust factories at remarkable speed. Several mechanisms are being explored. Massive supernovae at high redshift may produce dust very efficiently in their expanding ejecta. Rapid cycles of star formation and stellar death may have processed gas through stellar interiors many times in succession, building up heavy elements and dust in compressed timeframes. Some studies suggest that dust grains in the early universe may have grown not only inside dying stars, but also in the cold, dense gas of the interstellar medium itself, accumulating mass directly from the surrounding atoms. Each of these mechanisms, individually, has problems. Supernovae produce dust, but the grains must survive the violent reverse shocks of the explosions. Rapid star formation cycles require sustained, almost industrial efficiency. Dust grain growth in cold gas requires conditions that are themselves difficult to reproduce in early universe simulations. Combining these processes makes the picture more plausible, but it also paints an even more vigorous early universe, in which star formation, stellar death, and chemical processing all operated at speeds the standard model has trouble accommodating. The presence of early dust has implications beyond chemistry. Dust is also a building block of planets. Once enough dust has accumulated around a forming star, it can clump together, eventually forming planetesimals and planets. If dust formed early in cosmic history, then planets could have formed early as well. The first rocky worlds may have appeared not billions of years after the Big Bang, but only a few 100 million years after. Some astronomers have begun to wonder whether the first habitable conditions might have been possible far earlier in cosmic history than we have traditionally assumed. If true, this opens an unsettling possibility. Life, in some primitive form, might have had time to begin and disappear in regions of the universe billions of years before our own world emerged. We are not necessarily the first chapter of the cosmic biography. We may simply be one of the latest. None of this is yet certain. The early dust observations are themselves still being interpreted. But the very fact that early dust exists in such quantities is one more crack in the simple story of slow cosmic evolution. The cosmic dawn, in Webb's data, appears not just to have lit up the first stars and formed the first galaxies, but to have already begun assembling the raw materials of worlds. And as Webb has observed, some of those early galaxies are doing something even stranger than producing dust. They are shining far brighter than they have any right to. Among the strangest features of Webb's deep field surveys is the discovery of small early galaxies, modest in size but blazing with unexpected intensity. These tiny galaxies, often a fraction of the size of the Milky Way, sometimes shine with brightnesses that, at face value, suggest extreme rates of star formation. By certain measures, some of these galaxies appear to be forming stars hundreds of times faster than any modern galaxy of comparable size. They are tiny torches, lighting up the cosmic dawn with an intensity that does not fit any of the gentle starting conditions our textbooks predict. To produce such intense light, several explanations have been considered. One possibility is that these galaxies are simply caught in unusually busy moments of their early lives, brief bursts of star formation triggered by mergers or rapid gas inflows. Galaxies in the early universe were closer together than they are today, and small encounters were more frequent. Some of these tiny galaxies may simply be passing through bright phases that account for their unusual luminosities. Another possibility is that the brightness is not entirely from stars. Some of these galaxies may host young, growing supermassive black holes in their cores. The accretion light from a feeding black hole can be extraordinarily luminous, easily outshining the surrounding stellar population. If even a small fraction of these tiny galaxies host such central black holes, the apparent brightness of the population as a whole becomes easier to explain. This interpretation links back to the little red dots and the early supermassive black hole problem. The cosmic dawn in this picture is not just a galaxy era, it is a black hole era as well. A third possibility, more provocative, is that the first stars in these galaxies were themselves more luminous than the stars of today. If a substantial portion of the stellar population in these galaxies belonged to massive population 3 or near population 3 stars, the brightness per unit mass would be much higher than in modern galaxies. A galaxy of modest size could shine with an outsized brilliance simply because its stars individually emit more light. None of these explanations is fully satisfying on its own. The truth probably involves a combination. Some of the bright tiny galaxies are starburst galaxies in the middle of intense formation phases. Some host bright black holes. Some contain unusually luminous stellar populations. Together, these processes paint a portrait of the cosmic dawn as a place of intensity. The early universe was not a quiet nursery. It was a place where small things shone disproportionately bright, where black holes lit up little galaxies, where star formations surged in bursts, where chemistry advanced quickly in compressed time frames. It was, in a word, alive. And this aliveness has consequences for one of the most important phases of cosmic history, the moment when the universe transitioned from a dark, neutral fog into the transparent, luminous space we live in today. This transition is called Ryanization, and it is one of the great pivotal events in the cosmic timeline. After the Big Bang, the universe was hot and ionized, filled with free electrons and protons. As it cooled, those particles combined to form neutral hydrogen atoms, releasing the cosmic microwave background light as they did so. For several 100 million years afterward, the universe was filled with neutral hydrogen gas. This neutral gas was nearly transparent at most wavelengths, but it absorbed ultraviolet light strongly. Ultraviolet light is the kind that ionizes hydrogen, knocking electrons loose. As the first stars and galaxies and black holes formed and began emitting ultraviolet radiation, they slowly burned away the neutral hydrogen around them, ionizing it again. By the end of this process, the universe was once more fully ionized, but this time it was also transparent to most light, allowing photons to travel freely across enormous distances. This second ionization, replacing the original ionization that had cooled away, is what we call ryanization. The standard story of ryanization predicts a relatively gentle, gradual process, beginning around the time the first galaxies formed and continuing for hundreds of millions of years. According to this picture, ryanization should have been smooth, with bubbles of ionized gas slowly expanding and merging until the entire cosmic medium was transparent. James Webb, when it studied the era of ryanization in detail, found a far less gentle picture. The data suggests that ryanization was patchy, vigorous, and uneven. Some regions ionized quickly. Others remained neutral for surprisingly long. The transition, rather than being a smooth fade, looked more like a series of overlapping floods, with some areas of the universe blazing into transparency, while neighboring regions remained dark and opaque well into later eras. To produce this kind of patchy, intense reionization, the early universe must have contained sources of ionizing radiation more numerous and more luminous than the standard model predicted. Bright, tiny galaxies, supermassive black hole hosting little red dots, vigorous star formation in dense regions, all of these would contribute. The picture that emerges is consistent with the broader pattern Webb's discoveries have built. The cosmic dawn was loud. It was hot. It was uneven. It was creative. Ionization was not a soft, even sigh of light spreading across a quiet medium. It was a thunderstorm of photons, breaking through the early universe in scattered, brilliant flashes, eventually consuming the neutral fog, but doing so in fits and bursts, rather than a single, calm wave. This is not just a refinement of detail. It changes how we think about the formation of the first galaxies and the first habitable conditions. The intensity and patchiness of reionization affect how heat, ultraviolet light, and chemistry spread through the early universe. They affect where and when the first cool, dense regions could survive long enough to form stable structures. They affect the conditions under which the first dust grains formed, the first heavy elements spread, the first planets accreted. The cosmic dawn was not just bright. It was the stage on which all subsequent cosmic history was set. And Webb is showing us that this stage was already, in its first scenes, more complicated and more energetic than the script had predicted. There comes a moment in every long inquiry when the focus shifts. We have been looking outward, into the vast tapestry of cosmic structure, watching galaxies rise too quickly and black holes grow too large and dust settle into places it should not yet exist. But the universe is not only a story about scale, it is also a story about possibility. About the question that has followed humanity since the first eyes turned upward and wondered, are we alone? Webb was not built primarily to answer that question. It was built to study the universe in infrared, with all the breadth that purpose entails. But because of the way infrared light interacts with the atmospheres of distant worlds, Webb has, almost as a side effect of its design, become the most powerful instrument ever pointed at the question of life beyond Earth. And in the few short years it has been operating, it has already produced a hint that if it survives further scrutiny, may go down as one of the most significant chemical signals in human history. That hint came from a planet called K2-18b. K2-18b orbits a small, cool red dwarf star, roughly 120 light-years from Earth. It is a sub-Neptune, a class of planets that are common in our galaxy, but rare in our own solar system. It is somewhere between 2 and 3 times the radius of Earth, and roughly 9 times its mass. Its orbit places it in what astronomers call the habitable zone, the band of distance from a star where surface temperatures could allow liquid water to exist if other conditions are right. For years, K2-18b had been considered an interesting target for atmospheric study. Webb's spectroscopic capabilities allowed scientists to do something earlier instruments only dreamed of, to actually examine the chemical composition of its atmosphere by analyzing the starlight that filtered through it during transit, when the planet passed in front of its star. The first results were already remarkable. Webb confirmed the presence of methane and carbon dioxide in K2-18b's atmosphere, while finding very little ammonia. This particular combination is consistent with a class of worlds that some theorists have called Hycean planets. Hycean is a portmanteau of hydrogen and ocean, suggesting a planet with a hydrogen-rich atmosphere covering a global ocean of liquid water. Such worlds, if they exist, would be very different from Earth, but they could potentially harbor life. The atmospheric signature alone was a major scientific milestone. But what came next was the result that turned the discovery into a global headline. The Webb data showed a tentative hint of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by life, specifically by tiny ocean microbes called phytoplankton. There is no known geological process that produces it in significant quantities on a planetary scale. Its presence in an exoplanet atmosphere, if confirmed, would be one of the strongest possible biosignatures, a chemical fingerprint difficult to explain without invoking biology. The team behind the discovery was extraordinarily careful. They emphasized that the detection was tentative. The signal was weak. The data needed to be confirmed by additional observations. They also noted that, given the strangeness of K2-18b's atmosphere, there was a possibility that some unknown chemical process might produce dimethyl sulfide non-biologically on this world, in conditions that simply do not exist anywhere on Earth. Despite these caveats, the implications were staggering. For the first time in human history, a real chemical hint of possible life had been detected in the atmosphere of another world. Not a speculation, not a model, an actual measurement made by a real instrument on a real planet. Even if the signal turns out to be something other than life, the fact that we are now in a position to make such measurements at all is a profound shift in the history of science. The age of remote biosignature detection has begun. K2-18b is now one of the most studied planets beyond our own. Webb has continued to gather data on it. Other observation campaigns are planned. Models are being refined. The hope is that within a few years, we will know whether the dimethyl sulfide signal strengthens, fades, or shifts into something we can identify with certainty. Whatever the outcome, the precedent has been set. We can now reach across light years and ask, in chemical terms, whether something is breathing on the other side. And K2-18b is not the only world Webb has been listening to. There are many. Each one carries its own story, its own atmosphere, its own potential whisper. The galaxy is full of planets. We are only beginning to learn how to read them. Among the many exoplanets Webb has studied, one in particular has demonstrated, in dramatic fashion, just how much detail this telescope can extract from a distant atmosphere. Its name is WASP 39b. It is a giant planet roughly the size of Saturn, orbiting so close to its star that its year lasts only about 4 Earth days. Its atmosphere is hot, with surface temperatures soaring well past the boiling point of metals. By every measure, WASP 39b is an extreme alien world. It has no obvious connection to Earth-like conditions. But the very fact that it is large, hot, and well-positioned for transit observations made it an excellent target for Webb's atmospheric studies. And the results, when they came in, did not disappoint. Webb produced the most detailed exoplanet atmospheric spectrum ever obtained. It detected water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and crucially, sulfur dioxide. The sulfur dioxide detection was the headline. It was the first time this molecule had ever been confirmed in the atmosphere of a planet outside our solar system. But the way it formed was even more important than the fact of its detection. The sulfur dioxide on WASP 39b was being produced through a process called photochemistry, in which intense ultraviolet radiation from the host star breaks apart molecules and triggers new chemical reactions. This was the first time such a process had been confirmed in an exoplanet atmosphere. The implications go beyond a single molecule. Photochemistry plays a key role in shaping planetary atmospheres. On Earth, it is responsible for the ozone layer, which shields the surface from harmful ultraviolet radiation and is itself essential for the kind of chemistry that allows complex life to thrive. By detecting active photochemistry on WASP-39b, Webb has demonstrated that the atmospheres of distant worlds are not static layers of gas. They are dynamic chemical environments, evolving under the influence of starlight, capable of producing molecules that would never have appeared without those photons. This matters for the search for life. To recognize a true biosignature, scientists need to understand what chemistry stars and atmospheres produce on their own, without biology. They need to map the photochemistry of various world types so that anomalous signals that cannot be explained by stellar radiation alone, can be flagged as potentially biological. WASP-39b, while not itself a habitable world, is becoming a benchmark for understanding the photochemistry of giant planets. Similar studies on smaller, cooler worlds are now underway. The toolkit Webb is developing for extreme worlds will eventually be applied to gentler ones, where the question of habitability becomes meaningful. WASP-39b has also revealed cloud structures, atmospheric layers, and dynamics that earlier instruments could not see. Its winds and pressure profiles can be inferred from the data. Its day-night temperature contrasts can be measured. Each of these properties, in turn, helps refine the models of how planetary atmospheres behave under a wide range of stellar and orbital conditions. The science of exoplanet atmospheres has, almost overnight, moved from a frontier where we struggled to detect anything at all to a discipline where we can resolve dynamic chemistry across millions of miles of intervening space. Webb has not just discovered new worlds, it has begun to teach us how worlds work. And among the worlds it is now turning toward are some of the most important targets in the entire search for life. The 7 rocky planets of a system called TRAPPIST-1. About 40 light-years from Earth in the constellation Aquarius sits a small, faint red dwarf star known as TRAPPIST-1. By human standards, the star is dim. It emits about 1/10 the light of the Sun, and only about 0.5% its energy. To find a planet orbiting such a faint star, you must look very carefully. But what astronomers found there was not just a planet. It was an entire family. 7 rocky worlds orbit TRAPPIST-1, packed tightly into a region smaller than the orbit of Mercury around our own Sun. 3 of them lie within the habitable zone, where surface conditions could potentially allow liquid water. The TRAPPIST-1 system has, since its discovery, been one of the most studied targets in modern astronomy. It offers something almost no other system does: a direct comparison of multiple rocky worlds at varying distances from a single star, all viewable with current instruments. The system is, in effect, a natural laboratory for understanding how planets evolve under similar conditions. James Webb has now turned its instruments toward this system, beginning the long process of studying its planets in detail. The first results focused on the innermost worlds, TRAPPIST-1b and TRAPPIST-1c. These planets orbit closest to their star and receive the most stellar radiation. The data suggested that neither of them retains a significant atmosphere. They appear to be bare, sun-baked surfaces, probably stripped long ago by the intense radiation and stellar flares of their host star. This was a sobering finding. Red dwarf stars, while abundant in the galaxy, are also often violent. They can produce powerful flares that may strip the atmospheres from nearby planets. If the inner TRAPPIST-1 worlds have lost their atmospheres, the question becomes whether the outer worlds, farther from the star, have managed to keep theirs. The early answers, while preliminary, are cautiously hopeful. Webb's observations suggest that some of the outer TRAPPIST-1 planets may indeed retain atmospheres. The data is still being refined. The signals are subtle, requiring many observations to confirm. But the possibility that even one of the planets in the habitable zone of TRAPPIST-1 might have a substantial atmosphere is one of the most important leads in the search for life beyond Earth. If atmospheres are confirmed, the next step will be to study their chemistry. Are there water vapor signatures? Are there carbon dioxide bands? Are there any molecules that suggest active chemistry of an unusual kind? Each spectrum will be examined with care. Each measurement will be weighed against models and against possible biases. The TRAPPIST-1 system also offers a chance to understand the variability of planetary outcomes. The 7 worlds formed in roughly the same conditions, from the same disk of gas and dust around the same young star. Yet their fates have diverged. Some have lost their atmospheres entirely. Others may have retained them. Some may have surface oceans of water. Others may be desiccated, frozen, or geologically inactive. By comparing them, scientists hope to learn what factors determine whether a rocky world becomes habitable, sterile, or somewhere in between. This is essential information for the broader search for life. The galaxy contains billions of red dwarf stars, many of which likely host planets. If we can understand which conditions in such systems lead to habitable worlds, we can prioritize where to look. We can build target lists. We can sharpen instruments and observation strategies. The TRAPPIST-1 system is small, faint, and close. It is exactly the kind of laboratory the search for life needs. And Webb is, at this moment, the only instrument capable of conducting these experiments at the level of detail required. Each new TRAPPIST-1 observation, then, is more than a measurement. It is a piece of a larger answer to the oldest question humans have ever asked. Are we alone? The data is still coming in. The verdict, for now, is that we do not yet know. But the question has never before been asked with such precision. If you have come this far through the long descent, take a slow breath. Let the room around you remain where it is. We have walked through galaxies that should not have formed, and stars whose age cannot be reconciled with the cosmos around them. We have stood beside black holes that grew too quickly and lights that arrived from impossible distances. We have looked at planets whose atmospheres are beginning, ever so faintly, to whisper. There is no need to remember any of it perfectly. The point of this kind of journey is not memorization. It is the slow softening of the boundary between you and the night. The gentle reminder that the universe is not happening somewhere else. It is happening here, around you, inside the same physics that holds your bones together, and the same chemistry that drives your thoughts. If this journey has been keeping you company in a way that matters, you might leave a small comment under the video, even just a single word, so that the algorithm and I both know you are still here, still walking with us through the dark. There is no obligation. The stars do not require it. But if it pleases you, it would mean a great deal. There are objects in the universe that resist the categories we built for them. They are not quite stars. They are not quite planets. They occupy a strange middle band of mass and temperature, smoldering quietly across cosmic time, sometimes alone, sometimes in pairs, sometimes drifting between stellar systems with no obvious origin. These objects are called brown dwarfs, and Webb has been finding them in places and in numbers that are quietly reshaping how astronomers think about cosmic chemistry. A brown dwarf forms much like a star from a collapsing cloud of gas. But where a star reaches enough mass for sustained hydrogen fusion in its core, a brown dwarf does not. Its mass falls below that threshold, leaving it warm but not stellar. It glows with leftover heat from its formation, slowly cooling over billions of years. From the outside, a brown dwarf can look like a faint, oversized planet. From the inside, its physics is closer to the structure of a small star without ignition. They occupy a fascinating boundary. The line between a giant planet and a small brown dwarf is fuzzy. The line between a large brown dwarf and a tiny star is also fuzzy. As Webb has surveyed nearby star-forming regions and the deep field, it has produced a richer census of these objects than ever before. Some are found in young stellar nurseries, embedded in the gas clouds where they formed. Others are found floating freely between stars, with no apparent parent system. These are the rogue brown dwarfs, drifting through interstellar space alone. The fact that there are many of them is itself a puzzle. To form a brown dwarf, you need a localized region of gas to collapse under its own gravity. In the simplest models, this is hard to do without the help of a larger forming system, where gravitational interactions can fragment the gas into multiple pieces, some of which become stars and some of which become smaller objects. Producing enough rogue brown dwarfs to match Webb's findings requires either that some of them were ejected from their original systems through gravitational encounters, or that smaller, isolated gas clouds can collapse into brown dwarfs more easily than current models suggest, or both. The atmospheres of these rogue brown dwarfs are also surprising. Some show signs of methane, water vapor, ammonia, and clouds of various exotic compositions. Others appear to have weather patterns, wind belts, temperature variations, storm systems. They are, in many ways, miniature gas giants without parent stars. By studying them, scientists are building a new framework for understanding planetary atmospheres in extreme isolation. There is also the question of age. Some Webb-observed brown dwarfs appear extraordinarily old, with chemical signatures suggesting they have been drifting through the galaxy for nearly the entire age of the universe. Their slow cooling makes them ideal cosmic timekeepers, reflecting in their atmospheres the conditions of the gas clouds in which they formed billions of years ago. Each ancient brown dwarf is a fossilized clue to early galactic chemistry. Together, they form a record that complements the information astronomers gather from stellar populations and interstellar dust. There is, finally, a more philosophical reason these objects matter. They blur the distinctions we have inherited. The neat boxes of star, brown dwarf, and planet do not fully capture what nature actually produces. The universe creates a continuum of objects with various combinations of mass, temperature, and history. Webb is showing us that this continuum is denser, stranger, and more populated than we had imagined. The galaxy is full of orphans, drifting silently, carrying with them, in their gentle infrared glow, the memory of stellar nurseries that no longer exist. There is a theme that has been building through everything we have explored, and now it deserves to be stated plainly. The universe Webb is showing us is not the universe we had inherited from textbooks. It is older than expected in some ways, faster than expected in others, more chemically advanced, more structurally organized, more aggressively luminous, more full of giants in places where giants should not yet have grown. Each anomaly, taken on its own, can be explained with a careful adjustment. But together, they push toward something larger, something that may eventually require revising one of the most important ideas in modern cosmology. That idea is called inflation. Cosmic inflation is the proposal, developed in the early 1980s, that the universe underwent a brief but extraordinary phase of accelerated expansion in the first tiny fraction of a second after the Big Bang. During this phase, the universe is thought to have stretched by an enormous factor, smoothing out any large-scale irregularities and amplifying tiny quantum fluctuations into the seeds of all later structure. Inflation, as a framework, is enormously successful. It explains why the universe looks remarkably uniform on the largest scales. It explains why distant regions of the cosmos appear to have similar temperatures and densities, even though they are too far apart to have ever exchanged information at light speed. It explains the spectrum of fluctuations seen in the cosmic microwave background. It is one of the great theoretical accomplishments of the late 20th century. But inflation, in its standard form, also makes specific predictions about how structure should grow after the inflationary phase ends. It predicts a particular pattern of initial fluctuations, a particular rate of structure formation, a particular smoothness on small scales. Webb's data, combined with other observations, is beginning to gently strain some of these predictions. The early universe Webb is showing us was already busy assembling massive galaxies, supermassive black holes, and complex chemistry far faster than the simplest inflationary scenarios would suggest. Either the initial conditions left by inflation were slightly different from what the simplest models predict, or the post-inflationary growth of structure proceeded in ways that involve physics not yet incorporated, or inflation itself, in some of its details, may need to be revised. Several alternative scenarios have been proposed. Some involve modifying inflation to leave behind slightly larger initial fluctuations on certain scales, which would naturally produce earlier and more massive structures. Others involve adding a brief period of additional expansion or alternative early dark energy, which can shift the timeline of structure formation. Still others are more radical, suggesting that inflation may not have been a single smooth event, but a more complex series of phases, leaving subtle imprints in the cosmic structure that we are only now beginning to detect. These ideas remain speculative. The standard inflationary picture is still the best framework available, and it accounts for an enormous amount of data. But the field has begun to take alternatives more seriously than it did even a decade ago. Webb, simply by sharpening our view of the early universe, has contributed to this opening of theoretical space. We may be approaching a moment in cosmology when the standard model receives its first serious revision since inflation itself was added to it. Or we may not. The data is still accumulating, the picture is still forming. But the very fact that the question is being asked at all is a sign that something important is shifting beneath the surface of the field. There is one more piece of evidence that fits into this larger pattern, and it concerns the ancient light that has long been considered the cleanest source of information about the early universe. The cosmic microwave background. Released about 380,000 years after the Big Bang, this faint glow fills the sky with a nearly uniform temperature of just under 3 degrees above absolute zero. It is the oldest light we can see. It has been mapped with extraordinary precision by satellites like COBE, WMAP, and Planck. The patterns of its tiny temperature fluctuations have, more than any other dataset, calibrated the standard cosmological model. For decades, the cosmic microwave background has appeared to confirm the standard model in essentially every detail. Its statistics match predictions. Its overall uniformity matches predictions. Its temperature pattern matches predictions. But, as instruments have improved, faint anomalies have begun to surface. Several large-scale features in the cosmic microwave background appear, by very careful statistical analysis, to be unusual. There are patterns of alignment in the largest scale fluctuations that do not match simple isotropic predictions. There are unexpectedly cold and warm spots. There are subtle preferred directions that hint at a cosmic structure not fully accounted for in the standard model. These anomalies have, for years, been treated cautiously. Some scientists argue they are statistical flukes, the kind of occasional unusual features that any random distribution would produce by chance. Others argue they are hints of new physics, traces of phenomena from the early universe that the standard model does not capture. Webb's discoveries, while not directly imaging the cosmic microwave background, are reshaping the context in which these anomalies are interpreted. If the early universe was less smooth than expected, if structure formed more aggressively, if anisotropies in galaxy spins and cosmic Webb alignments are real, then the cosmic microwave background anomalies become more interesting. They are no longer isolated curiosities. They become potentially related to a broader pattern of mild but persistent deviations from the simplest cosmological assumptions. Several theories try to connect these dots. One suggests that the very earliest universe, perhaps during inflation itself, had subtle anisotropies that have left fossil imprints in both the cosmic microwave background and in the later distribution of structure. Another suggests that the early dark energy proposed to address the Hubble tension might also leave faint signatures in the cosmic microwave background that align with some of the observed anomalies. Still, other theories suggest that the universe might not be exactly flat, or that gravity itself might have subtly different behavior on the very largest scales. None of these ideas is yet conclusive, but they are no longer dismissed automatically. The combined weight of Webb's discoveries and the cosmic microwave background anomalies has created a kind of theoretical pressure that the field is taking seriously. Cosmology is, in a sense, listening. Listening for small voices in the data that, taken together, might be saying something important. And one of the things that voice may be telling us is that the universe is not as perfectly symmetric as we have always assumed. The phrase is unsettling when said directly. The universe leans. By every careful measurement, the leaning is small. By every standard test, the universe still appears very nearly isotropic. But the cumulative evidence from galaxy spin asymmetries, cosmic microwave background alignments, large-scale structure orientations, and now Webb's observations of distant cosmic Webb filaments is beginning to suggest that there may be a faint, hidden tilt in the cosmic order. If this tilt is real, it changes the way we think about the early universe. The simplest cosmological models assume that the universe is statistically symmetric in every direction. There should be no preferred axis. There should be no cosmic plane of structure. Any apparent asymmetries should average out as we look at larger samples. The observations Webb is contributing to suggest that this averaging is incomplete. There is a faint preference, a faint orientation, a faint tilt that does not vanish even in the largest available samples. Several explanations have been proposed. The simplest and most boring is that the apparent tilt is an artifact of how we observe the universe, biased by selection effects, instrumental quirks, or limitations in sample size. This explanation cannot yet be ruled out. As more data accumulates, it remains possible that the tilt will fade away. A more interesting explanation is that the early universe genuinely did have a preferred direction. This could have been imprinted during inflation by some asymmetric quantum field, or it could be a fossil from an even earlier phase that inflation did not entirely smooth out. If real, such a tilt would force a deep revision of cosmological theory, since most current models assume perfect isotropy from the start. A third explanation, more speculative still, suggests that the universe may be slowly rotating on cosmic scales. If the entire cosmos rotates, even very slowly, it would imprint a faint preferred direction in the orientation of structure. Such cosmic rotation has been considered in alternative cosmological theories, but it is not part of the standard model. Webb's data does not yet confirm any of these explanations. The evidence is suggestive, not decisive, but the cumulative pressure is building. Cosmology, more than at any time in the last several decades, is open to the possibility that some of its foundational assumptions need to be re-examined. The universe Webb is showing us is one in which the apparent balances and symmetries of the standard model are not quite as robust as we believed. The cosmos is not visibly asymmetric, but it is not perfectly symmetric either. And in cosmology, even the smallest cracks at the foundation can eventually require an entirely new building. Let us return for a moment to the icy worlds that float much closer to home. Among the most exciting places in our own solar system, the ones where life might exist beyond Earth, are not the warm, rocky planets, but the cold moons. Bodies like Europa, Enceladus, Ganymede, and Triton hide beneath their frozen surfaces vast subsurface oceans of liquid water. These oceans, kept warm by tidal heating from their parent planets, may contain the same essential ingredients that allowed life to emerge on Earth. Webb has been adding new chemistry to our understanding of these worlds. Its observations of Europa, the ice-covered moon of Jupiter, have detected carbon dioxide on its surface. Most importantly, the carbon dioxide appears to come from the moon's interior, suggesting that material from the subsurface ocean has reached the icy crust. This is a critical clue. If chemistry from Europa's hidden ocean is leaking onto its surface, then Webb and future instruments may eventually be able to study that ocean's composition without needing to drill through miles of ice. The chemistry detected so far is consistent with the kind of environment that could support simple life. Whether life actually exists, there is another question entirely. But the conditions, by every available measure, remain plausible. Webb has also studied Enceladus, the small Saturnian moon famous for the plumes of water vapor and ice it shoots into space through cracks in its surface. These plumes connect directly to its subsurface ocean. They have already revealed water, methane, ammonia, and complex organic molecules. With Webb's higher resolution, the chemistry of these plumes is becoming clearer. The picture that emerges is of an ocean rich in the kinds of molecules that, on Earth, are associated with the chemistry of life. Whether life is actually present, there remains unknown. But Enceladus has, for years, been one of the most promising candidates for finding microbial life beyond Earth. Webb is making the case for that candidacy stronger. Ganymede, the largest moon in the solar system, also harbors a subsurface ocean, possibly larger than Europa's. Its surface chemistry, while less well studied, is consistent with interactions between deep ice layers and hidden water reservoirs. Webb's data has helped refine our understanding of Ganymede's outer ice shell and its possible coupling to the ocean below. Triton, the largest moon of Neptune, presents perhaps the most intriguing case. It orbits its planet in retrograde, suggesting it was captured from the outer solar system long ago. Its surface contains nitrogen ice geysers and signs of geological activity. Beneath it may lie a liquid layer driven by tidal interactions or radioactive heating. Webb's observations have revealed surface chemistry consistent with active processes between the surface and the interior. Triton, often overlooked in favor of its more famous cousins, may be one of the most fascinating destinations in our own solar system. None of these worlds is easy to study. Each one is far away. Each one is hidden beneath layers of ice. But Webb has, in its short operational lifetime, already added significant detail to our understanding of all four. And in doing so, it has helped reframe a profound question. Life may not be confined to warm, sunlit planets like Earth. It may flourish, if it exists at all, in the cold and dark, beneath thick crusts, fed by chemistry that has nothing to do with sunlight. The galaxy is full of such worlds, and the techniques Webb is honing on the icy moons of our own solar system will eventually be applied, in modified form, to similar worlds around other stars. There is another single object Webb has observed that deserves its own quiet chapter, because it is the kind of discovery that captures the imagination as much as it advances the science. It is a star. A single, distant, lonely star. Its name, given by the team that first identified it, is Earendel. Earendel was originally discovered by the Hubble Space Telescope, which spotted a faint streak of light along a gravitational lensing arc behind a massive galaxy cluster. The cluster's gravity was acting as a giant lens, bending and magnifying the light from objects far behind it. In one of those magnified images, Hubble noticed a star. Just one star. Not a galaxy, not a cluster, but a single point of light, distinguishable from its surroundings. The light from Earendel had been traveling for about 12.9 billion years. At that time, the universe was less than 1 billion years old. Without the gravitational lens, no telescope on Earth could possibly have resolved this star. With the lens, Hubble caught a glimpse, and Webb came along afterward to confirm the discovery and add detail. According to Webb's analysis, Earendel may actually be a binary star system. Two enormous, hot, blue stars orbiting each other, together carrying many dozens of solar masses, possibly hundreds. Their light, magnified by the lens, has crossed nearly the entire history of the universe to reach us. To stand under the night sky and know that Webb has captured the photons of an individual star from a time when galaxies were still finding their shape is a strange and powerful feeling. Earendel is not just a record holder, it is a window. The chemistry of its light tells us about the conditions of star formation in the cosmic dawn. Its possible binary nature speaks to the dynamics of stellar systems in the early universe. Its very existence reminds us that even individual stars, normally far too faint to study at such distances, can be made visible by the alignments of cosmic geometry. As Webb continues to scan known lensing fields, more such discoveries are likely. Each new lensed early star adds another data point. Each spectrum tells another small piece of the cosmic chemistry story. Each lonely point of light is, in its way, a messenger from the dawn. Earendel was the first of these messengers to be confirmed. It will not be the last. And as more arrive, our picture of the very first stars and stellar systems will sharpen, even if we never see population 3 stars themselves in the simple, isolated way the textbooks once promised. There is another puzzle running quietly through the data, one that connects to the dark matter mystery, but takes a different angle into it. It is the puzzle of how galaxies rotate. For nearly a century, the rotation of galaxies has been one of the strangest pieces of evidence in modern astronomy. When astronomers measure how fast stars and gas move at different distances from the center of a galaxy, they consistently find something that does not fit the visible mass alone. According to ordinary physics, stars in the outer regions of a galaxy should orbit more slowly than stars near the center, in the same way that Neptune orbits the Sun more slowly than Mercury does. Yet, in galaxy after galaxy, the outer stars move at speeds that match or even exceed those of the inner stars. The rotation curves stay flat instead of falling off. To keep these outer stars bound to their galaxies, there must be additional, unseen mass providing extra gravity. This unseen mass is what we call dark matter. The standard interpretation of these flat rotation curves has been one of the foundations of dark matter cosmology. Webb has now sharpened our view of galaxy rotation in unprecedented detail. By studying the motion of stars and gas in distant galaxies, including some in the early universe, it has produced rotation curves at a level of precision that Hubble could only approximate. The results are mixed in a meaningful way. Some early galaxies show rotation curves consistent with what dark matter halos would produce. Others show subtler patterns. Some appear to have rotation curves that decline toward the outer regions, more like the patterns predicted by visible matter alone. Others appear to behave more like modern galaxies, with flat or rising curves indicating substantial dark matter halos. The diversity is itself surprising. The standard cosmological picture predicts that early galaxies should all be embedded in massive dark matter halos that contribute most of their mass. The Webb data suggests that the relationship between visible and dark mass in early galaxies may be more complicated than this. Some galaxies seem to have less dark matter relative to their visible content than expected. Others seem to have more. Some show signs of unusual gravitational behavior that does not fit either picture cleanly. This complexity has revived interest in alternative theories of gravity. Modified Newtonian dynamics, or MOND, was proposed in the early 1980s as an alternative to dark matter. It suggests that at very low accelerations, the law of gravity itself behaves slightly differently than Newton and Einstein predicted. MOND can reproduce the flat rotation curves of galaxies without invoking unseen mass. For decades, MOND has been considered a fringe alternative, gaining traction in some areas, struggling to explain phenomena like the bullet cluster in others. But Webb's discovery of unusual rotation patterns in early galaxies has, for some researchers, given MOND-like ideas a fresh look. There are now hybrid theories that combine elements of dark matter and modified gravity, attempting to explain both the cluster-scale evidence for unseen mass and the galaxy-scale anomalies in rotation. None of these ideas is yet accepted as a replacement for dark matter. The cluster evidence remains very difficult to explain without it. But the rotation puzzles in early galaxies are now part of a broader conversation about how gravity behaves on different scales and in different cosmic eras. Webb has not so far told us whether dark matter is real or whether gravity itself behaves unusually. What it has done is sharpen the questions. The data is becoming precise enough that the simplest forms of both standard cold dark matter and pure modified gravity are starting to feel inadequate. The truth, when it eventually emerges, may involve elements of both, or something else entirely. The galaxies, in their patient rotations, are telling us a story we have not yet learned to read. There is a strange comfort in admitting that science does not yet have all the answers. It is the kind of comfort you find in honesty, the kind that allows curiosity to remain alive instead of being replaced by certainty. Cosmology, at this moment, is in a state of confessed not knowing on multiple fronts. The Hubble tension has not been solved. The early universe puzzles have not been resolved. The dark matter problem remains open. The early supermassive black holes are not yet explained. The population 3 stars have not been found. The cosmic web's early assembly is poorly understood. The galaxy rotation diversity is not yet accounted for. The chemistry of the cosmic dawn requires unfamiliar mechanisms. The very age of the universe is being subtly questioned. And the cosmic microwave background harbors anomalies that may or may not be statistical flukes. Each of these puzzles, individually, is the kind of problem a generation of physicists could spend a career trying to solve. Together, They form a portrait of a field on the edge of transformation. There have been moments like this in the history of physics before. The late 19th century was such a moment. Classical physics seemed nearly complete, but a few small anomalies, like the orbit of Mercury and the spectrum of black body radiation, refused to be fit into the standard framework. Those small anomalies, when finally addressed, gave birth to relativity and quantum mechanics, the two greatest revolutions in 20th century science. Cosmology may be standing at a similar threshold. The Standard Model has had a remarkable run. It explains a vast amount of data with elegant precision. But the cracks Webb is revealing are persistent. They are not isolated. They appear connected. They suggest that something deeper than parameter tuning is at work. The next steps in cosmology will likely involve a careful examination of all of these puzzles together, rather than separately. The patterns they form may turn out to be the most important clue we have. Maybe the universe is older than we thought. Maybe dark matter behaves differently than we believed. Maybe gravity has subtle features we have not measured. Maybe inflation needs revision. Maybe the very symmetry assumptions that underlie cosmology need to be relaxed. Maybe several of these things are true at once. Whatever the answer, it will likely involve a synthesis. A new framework that does not throw away the successes of the Standard Model, but extends it, the way relativity extended Newton's mechanics, or quantum mechanics extended classical wave theory. We are not throwing the chair away. We are noticing that it has been hovering for a while, and asking what is holding it up. And in noticing, we open the door to learning something new. Webb is the instrument that has made this noticing possible. It has not given us a new theory. It has given us better data. Better data is what every revolution begins with. The careful observations Webb is making across the universe, from the cosmic dawn to the icy moons of our own solar system, are the raw material of whatever cosmology will look like in 50 years. We are living through the beginning of that next chapter. Most of the time, the people who live through such transitions do not realize they are doing so until afterward. We are lucky in this respect. We can see, more or less in real time, that something significant is happening. The data is not subtle. The discoveries are not abstract. They are arriving every few months, each one nudging the picture, each one inviting us to update our understanding a little further. The universe is teaching us, slowly and patiently, that it is not what we thought it was. And the part of that lesson which surprises everyone, including the scientists themselves, is that it is teaching us with so much patience. The cosmos does not punish wrong models. It simply waits for better ones. It will continue waiting. And it will continue every time we look, to reward careful attention with quiet, decisive answers. There is a way of thinking about science, especially cosmology, that imagines the goal is to arrive at a final, complete description of reality. The dream of a theory that explains everything. Some great minds in physics have spent their lives chasing that dream. There is real beauty in it. The hope that all the layers, all the puzzles, all the anomalies will eventually fit into a single, harmonious framework, like a poem in which every line locks into place. But there is another way of thinking about it. The goal of science, in this other view, is not to arrive at completeness, but to keep arriving. To keep listening to the universe, keep refining our questions, keep producing instruments that can hear what we have not yet heard. From this perspective, cosmology has not failed simply because Webb has revealed cracks in the Standard Model. Cosmology has succeeded. It has built an instrument capable of detecting cracks that nothing before could detect. It has assembled a community of scientists patient enough to grapple with the cracks honestly. It has resisted the temptation to dismiss anomalies as noise. It has, in short, behaved in the way good science should behave. The reward for this behavior is not always satisfaction. Sometimes the reward is more uncertainty, more questions, more work. But it is also occasionally a moment of genuine discovery. A moment when something previously hidden becomes visible. A moment when a long-held assumption gives way to a new understanding. Webb has produced many such moments already, and it has been operating for only a few years. The mission is expected to continue for at least another decade, possibly longer. In that time, much more will be observed. Some current puzzles may be resolved, others may deepen. New mysteries, not yet imagined, may emerge. Each will contribute in its own way to the slow shaping of the next cosmology. And the wonder of it is that all of this is happening while you sleep, while you walk to work, while you wait for a bus. The universe is being learned by people you will never meet, in offices and observatories scattered around the world, using instruments you will never touch. The discoveries trickle out, one by one, in papers most of us never read, in articles half of us never finish. And yet, slowly, the picture changes. The cosmos we will hand to our grandchildren will not be the same cosmos we inherited. It will be richer, stranger, less symmetrical, more full of mysteries we have at least begun to name. There is a quiet honor in being alive while this is happening. You are part of a generation that has watched the first deep-field images from the most powerful infrared telescope in history. You are part of a generation that has seen the first credible chemical hint of life beyond our solar system. You are part of a generation that may, within its lifetime, see the verdict on dark matter, the resolution of the Hubble tension, the discovery of the first confirmed biosignature on a distant world. None of these things were available to anyone before us. We did not earn them. We simply happened to be here at the right time. And being here, the least we can do is pay attention. Pay attention to the slow reshaping of the universe by those who study it. Pay attention to the quiet revolutions happening in journals and conferences. Pay attention to the night sky, even if you cannot see most of what Webb sees, because the sky has not changed in a meaningful way for billions of years, and we are the first creatures to have the tools to read it carefully. The stars overhead are the same stars our ancestors saw, but the story they tell is now beginning to be heard. Webb has given us better ears. Whatever it tells us next, we will be ready to listen. There is one final question that always returns when discussions like this go on long enough. The question is whether any of this, the cosmic dawn anomalies, the early black holes, the leaning universe, the chemistry that should not be there, has any meaning for ordinary life. Whether the strangeness of the cosmos has anything to do with the strangeness of being a person, walking around on a small planet in a quiet hour, trying to make sense of a single day. The honest answer is that the relationship is subtle. Cosmology will not pay your bills. It will not heal your relationships. It will not, by itself, make you happy. But it does something that is harder to name and easier to forget. It places you. It tells you, in measurable language, that you are a part of something enormous, that the carbon in your cells was made in stars, that the iron in your blood came from supernovae, that the calcium in your bones spent billions of years drifting through interstellar space before being incorporated into a planet that became your home. Cosmology, properly understood, is not a story about the universe. It is a story about your origins. The earliest galaxies Webb has imaged are the ancestors of your ancestors. The first stars that scattered heavy elements were the great-grandparents of every breath you take. The cosmic web is the framework on which your existence was eventually woven. There is no separation between the universe and you. The universe wove you. And tonight, while you have been listening, this same universe has been quietly turning. The light from countless distant galaxies has been arriving at the upper atmosphere of the Earth, scattering, fading, traveling onward into the dark. New stars have been igniting in distant nebulae. Old stars have been sighing out their final layers of gas, seeding future worlds with the products of their long lives. Dark matter, in all its mysterious behavior, has been gravitationally shaping the cosmic web around galaxies you will never see. And somewhere, perhaps on a planet around a small red dwarf, some chemistry might be doing something that, if we were close enough, we would call life. We do not know yet. We will one day, perhaps. The point of this kind of thought is not to settle anything. It is to widen the window through which you look at your own life. The world we inhabit, with all of its difficulty and tenderness, is a tiny pocket of awareness inside a far larger story. To know this is to gain a kind of perspective that no other study quite provides. Not detachment, not indifference. The opposite of those. A deeper rooting in the fact that you exist at all, here now, capable of asking questions about a universe that, by every standard, did not have to be hospitable to questions. The universe is hospitable. It has produced you. It has produced the eyes you read with and the mind you read with. It has produced the very capacity to wonder about itself. That capacity is one of the rarer ingredients of the cosmos as far as we can tell. And as long as it is in you, you carry a fragment of the universe's most unusual property, which is the ability to know itself. Webb is, in a sense, an extension of that ability. An eye built by minds that the universe produced, looking back at the universe to learn what it has been doing for 13 billion years. The fact that this is possible at all is a miracle of a quiet kind. Not the kind that suspends the laws of nature, the kind that uses them fully to produce something the laws never had to permit. Let us return for a final, slow walk through what we have seen tonight, not to summarize, but to feel the weight of it. We began with a small image, a slice of sky no larger than a grain of sand. Inside that grain, thousands of galaxies waited. Some were close, familiar shapes glowing in the gentle distances. Others were far, deeply far, their light warped by the long journey, their forms older than the dust under our feet. We learned that those distant galaxies, the ones at the edge of the image, were not what cosmology had expected. They were too bright, too organized, too rich in chemistry, too quick to grow. We learned about a class of objects called the universe breakers, galaxies whose mass strained the standard model nearly to its breaking point. We followed the light of disks that should not have spun so early, of black holes that should not have grown so quickly, of small, intensely red dots that hint at relationships between black holes and galaxies very different from anything we see today. We faced the Hubble tension, the careful disagreement between two ways of measuring how fast the universe is expanding. We considered the idea that the universe might be older than we have written down. We followed the cosmic web back to its earliest assembly, finding it more developed than the standard models had foreseen. We looked at the absence of expected dwarf galaxies and the presence of unexpected anisotropies in galaxy spins, and we considered, gently, the possibility that the universe leans, however softly, in a direction we have not yet identified. We turned toward worlds. K2-18b, with its tentative whisper of dimethyl sulfide, an organic chemical signal that may be a hint of life. WASP-39b, with its sulfur dioxide and active photochemistry, the first confirmed example of a chemical reaction shaping an exoplanet atmosphere through starlight. The TRAPPIST-1 system, with its 7 rocky worlds, 3 of them inside a habitable zone, whose atmospheres Webb is patiently characterizing one by one. We met Arundel, a single distant star observed through gravitational lensing, the most far-flung individual star ever captured, whose light has been traveling for nearly the entire age of the universe. We considered the icy moons of our own solar system, Europa and Enceladus and Ganymede and Triton, whose subsurface oceans may host conditions for life and whose surface chemistry Webb has been quietly mapping. We thought about brown dwarfs drifting alone through interstellar space, blurring the boundaries between stars and planets. We turned, finally, to the deeper cracks, the strain on cosmic inflation, the anomalies in the cosmic microwave background, the faint indications that the universe may not be perfectly symmetric, the galaxy rotation diversity that is reviving interest in alternative gravity theories. We acknowledged that the standard cosmological model, while still extraordinarily successful, is showing signs of incompleteness in ways that suggest we are at the edge of a new chapter in fundamental physics. And throughout all of it, we kept returning, however briefly, to the one quiet message embedded in every Webb observation. The universe is older, faster, and stranger than we have imagined. It built galaxies, black holes, elements, and structures earlier than we expected. It produced complexity from the first moments of cosmic light. It carries, in the directions of its rotations and the patterns of its filaments, faint signatures of features we have not yet learned to interpret. And it produces, on certain small planets in certain quiet corners, brief windows of self-awareness. Brief moments when the universe, through the eyes of its own products, looks back at itself and tries to understand. You are one of those moments, so am I. So are the scientists who built Webb, the engineers who folded its sunshield, the families that supported them, the readers and listeners who follow the discoveries from far away. We are all small places where the universe pauses and reflects. The reflections we produce are imperfect. They are partial. They are colored by our biases, our mortalities, our limited senses. But they are still reflections. And in reflecting, we participate, however modestly, in the same long process that has been unfolding since the first photon escaped the first cooling plasma 13.8 billion years ago. The universe is in the act of becoming aware of itself, and tonight, you have been a small part of that act. If you have stayed with this until the end, thank you. Truly. There is a particular kind of patience required to follow long journeys like this, and it is the same patience that good scientists carry when they study the universe. You have practiced it without realizing it. You have, simply by listening, kept company with a way of thinking that resists the easy and prefers the careful. That is a rare quality, and one the world quietly needs. If anything in this long descent has spoken to you in a way that mattered, please consider letting it stay with you for a little while before going on with your day or your night. The cosmos is not in a hurry. The discoveries Webb has made will still be there when you think about them tomorrow, and the day after, and the year after. They will continue to grow and shift and reveal themselves, slowly, the way all real understanding grows. If you would like to come back for more nights like this, the channel is here. There is no urgency to subscribe. There is no need to comment if you do not feel moved to. But if a small part of you wants to keep walking through the dark with this kind of careful, attentive company, you are welcome here. And the next of these long, patient stories will find you when you are ready. The stars are still waiting. They have been waiting longer than the entire history of life on Earth, and they will wait a great deal longer still. We are the brief. They are the patient. We can borrow some of their patience if we let ourselves. There is, perhaps, no more useful inheritance from cosmology than this. Not the equations, not the data, not even the discoveries, but the simple posture of a creature that has learned to look up and to keep looking and to not be afraid of the size of what it sees. Be well. Sleep softly if you are sleeping. Walk gently if you are walking. The night is long, and the universe is older than memory, and somehow, against every probability, you are here to listen to it. That is enough for tonight. That has always been enough. There is something worth pausing on before we close the night entirely about the way these images even reach us. The pictures Webb produces, the ones you may have seen on news websites, in magazines, scrolling past you on quiet evenings, are not photographs in the simple sense. They are translations. The light Webb collects is infrared. The human eye cannot see infrared. Our retinas, evolved over hundreds of millions of years on a sunlit planet with a yellow star, are tuned only to a narrow window of the electromagnetic spectrum. Below the red end, the light becomes warmth, invisible. Above the violet end, it becomes ultraviolet, also invisible. The vast majority of the universe's light, when measured across all wavelengths, is invisible to us. Webb sees in the infrared, and to share that sight with us, scientists must translate. They take the various infrared wavelengths the telescope has captured and assign each one a visible color. Long infrared becomes red. Shorter infrared becomes orange or yellow. The shortest, sometimes near-visible wavelengths become blue. The result is what astronomers call a false color image. The galaxies in the images glow in colors they do not actually emit, because they emit colors no human can see. The red of an early galaxy in a Webb deep field is, in a sense, not really red. It is a token, a stand-in, a representation of light that has traveled 13 billion years and shifted into wavelengths that our eyes were never designed to interpret. There is something poetic in this. The universe speaks in many voices, and we hear only a few. Webb has built us new ears, and the images we share are translations from a language we never learned to read directly. Looking at a Webb image is, in a small way, like reading a translated poem. The meaning comes through, often beautifully, but the original was written in a tongue that belongs to the cosmos itself, not to us. This thought, far from being a limitation, is a kind of invitation. The universe contains far more than what we can see. It always has. We have spent most of human history walking around inside a tiny window of perception, calling it reality. Reality, it turns out, is enormous. And every new instrument we build is not a way of making reality bigger. It is a way of making our window slightly less small. Radio telescopes opened a window. Ultraviolet observatories opened another. X-ray and gamma-ray telescopes opened more. Now Webb, in the infrared, has opened the deepest window into the cosmic past that we have ever had. There will be more. The Roman Space Telescope will open another window in different ways, surveying enormous swaths of sky to find rare objects. The Habitable Worlds Observatory, currently being designed, will look for the chemical signatures of life on dozens of nearby exoplanets. Ground-based giants like the extremely large telescope will, with their massive 39-meter mirrors, resolve features on planets and stars that have, until now, been mere points of light. Each new instrument adds to the chorus. Each one widens our small window just a little more. And each one continues the long, patient project of teaching the universe how to be heard by its own products. We are, in this work, both the scientists and the children of the scientists. The minds of the people who built Webb were assembled from atoms made in stars that lived long before any of us were possible. The eyes of those minds, looking back through Webb at the light of those same kinds of stars, complete a kind of cosmic loop. The universe makes the eyes that look at it. The light that those eyes catch was made by the same processes that, eventually, made the eyes. There is no separation. There is only a long sequence of events, stretched across billions of years, that happens to include, on this small planet, this brief moment when we sit and ask what it all means. The asking is part of the universe. The not knowing is part of it too. And perhaps so is the patience. Cosmology has a strange relationship with timescales. The universe is 13.8 billion years old. The Earth is 4.54 billion years old. Life on Earth is between 3.5 and 4 billion years old. The genus Homo is roughly 3 million years old. Modern humans are around 300,000 years old. Recorded history, by some measures, is around 5,000 years old. The James Webb Space Telescope has been operational for less than 4 years. Each step in this sequence is dwarfed by the one before it. We are, in this sense, very young. The instruments we use to study the cosmos are even younger. The questions we ask have been asked for, at most, a few thousand years. The framework of modern physics has existed for, at most, a few centuries. The standard cosmological model has existed for less than a century. And yet, in this brief window of attention, we have managed to assemble a remarkably consistent picture of the universe. We have measured its age, its composition, its expansion, its structure. We have identified its largest features and many of its smallest. We have built telescopes that can see almost to the beginning of cosmic light. The fact that we can do this at all is one of the most extraordinary achievements of any species we know about. It is also a reminder of how much remains undone. Webb is not the end of cosmology. It is one chapter, perhaps a transformative one, in a much longer book. The book itself may never be finished, and there is, paradoxically, a kind of peace in that. If the universe were simple enough to fully understand, it would also be simple enough to be exhausted, and there would be a moment beyond which there was nothing left to wonder about. But the universe is not simple. The deeper we look, the more layers we find. Each apparent answer opens new questions. Each mystery, once partially solved, reveals deeper mysteries beneath. The cosmos appears to be inexhaustible. This inexhaustibility may be the universe's most reliable property. There will always be something new to learn. There will always be a deeper question to ask. There will always be a horizon farther than the one we have already reached. This is not a defect. It is a gift. It means that future generations will not run out of mysteries. The children of children of children, however far we project, will still find themselves looking up at a sky that has not exhausted itself, asking questions that have not been answered. They will inherit the long, careful work that we are doing now, just as we have inherited the work of those before us. They will use instruments we cannot yet imagine. They will discover phenomena we cannot yet describe. They will perhaps see things that we, in our smaller windows, would have considered impossible. And they will, in turn, hand the work onward to whoever comes next. This is what science actually is, when stripped of its short-term glamour. It is a relay. A multi-generational, multicultural, multi-civilizational relay of careful attention. Webb is one runner in that relay. So is each scientist analyzing its data. So is each engineer maintaining its instruments. So in a quieter way, is each person who reads about its discoveries, who tries to understand them, who carries them, even briefly, into a daily life that is otherwise full of more immediate concerns. You, by listening tonight, have been part of that relay. You have given a small portion of your attention, your time, your energy, to the larger project of understanding the universe. That contribution is real, even if it does not feel large. The universe is built from very small contributions, layered together over enormous spans of time. Your attention tonight is one such layer. So is the attention of every other person who has ever paused, however briefly, to consider where they are. The night sky, viewed without instruments, looks much the same to us as it did to our distant ancestors. The same constellations, more or less, spin slowly across the seasons. The same planets wander among the same fixed stars. The same Milky Way arcs across the same sky on clear summer nights, far from city lights. None of that has changed in any meaningful human time. And yet, behind that unchanging surface, the universe Webb is showing us is in constant motion. Galaxies are colliding. Black holes are feeding. Stars are being born. Stars are dying. Planets are forming. Planets are being torn apart. Civilizations, perhaps, are doing whatever civilizations do, on worlds whose existence we cannot yet confirm. The night sky is, to our eyes, a still photograph. To our instruments, it is a constantly unfolding film, frame by frame, year by year, decade by decade. Webb captures one set of frames. Future telescopes will capture others. And the more we observe, the more clearly we see that the cosmos is not a finished place. It is an ongoing process. The universe is still becoming. Whatever it will eventually look like, whatever its full structure and its final fate, it has not yet arrived. We are watching, in real time, the middle of the universe's life. Some of what Webb shows us is, in a sense, ancient. The light from distant galaxies left them long ago. By the time it reaches us, those galaxies have continued to evolve, perhaps merging with neighbors, growing, fading, reshaping in ways we will only see when their newer light eventually arrives. We are seeing a snapshot, but a delayed one. The universe, by the time Webb finishes a long observation, has already moved on to whatever comes next. This temporal layering is one of the strangest aspects of cosmology. The sky is not a single time. It is a tapestry of times, woven together, with every line of sight reaching different cosmic eras at once. Look one way, and you are watching galaxies as they were billions of years ago. Look another way, and you are watching the sun as it was 8 minutes ago. Look in between, and you can see the moon as it was a second ago, the nearest stars as they were a few years ago, the Andromeda Galaxy as it was 2.5 million years ago, the Triangulum Galaxy as it was 3 million years ago, and so on, deeper and deeper, until you reach the cosmic microwave background, which is the universe as it was 380,000 years after its beginning. All of these times exist in your eye at once, when you look up at the night sky. You are not seeing space. You are seeing history, layered across distance, with each layer arriving at the present moment from a different past. Webb has the privilege of seeing more layers, and seeing them more clearly than any instrument before it. The depth of its vision is unprecedented. The richness of the layered history it gathers, every time it points at any patch of sky, is something no telescope has ever achieved. This is part of why its discoveries have been so transformative. It has not just shown us new objects, it has shown us new times. And those new times, when carefully read, do not match the simple stories we had told ourselves about how the universe assembled itself. The early times, the cosmic dawn times, were richer and more vigorous than our models predicted. The intermediate times were stranger, with disks and spirals appearing far earlier than expected. The transitions between these eras were less smooth, less tidy, more eventful than the standard model assumed. The universe, in its layered history, is more dramatic than its current quiet appearance suggests. The night sky is not still. It is paused in our perception, but in reality it is alive, shifting, growing, dying, being reborn, all the time, everywhere, in ways we are only beginning to learn how to perceive. There is, perhaps, no better moment to end such a journey than at the edge of new questions, with the discoveries already made still settling into our minds, and the discoveries yet to come still unimagined. We have walked tonight through some of the strangest findings of the most powerful telescope humanity has ever built. We have considered the cracks they reveal in the foundations of cosmology. We have listened to the gentle whispers of distant atmospheres, the silent records of frozen oceans, the patient glow of stars that have been traveling toward us for almost as long as the universe has existed. We have not solved anything tonight. We have not arrived at a new theory. We have not put any of the great puzzles to rest. What we have done is something humbler and in some ways more important. We have looked together. We have given a small portion of our attention to the long, patient work of understanding the cosmos, and in doing so, we have participated in the oldest activity our species engages in: looking up, wondering, being briefly aware that we are alive in a universe that, against every probability, somehow produced creatures who could ask why. The why has not been answered. The why may never be fully answered. But the asking is what makes us what we are. And tonight, by asking with a little more care than usual, you have honored something rare and good in yourself. The universe will continue, regardless of whether anyone is listening. But it is more interesting, somehow, when someone listens. Webb is listening, in its way, with infrared eyes and patient electronics. The astronomers who study its data are listening, with careful methods and slow papers. And you, in your own way, by following along through the long descent of this story, have been listening too. Listening is enough. It does not need to lead anywhere. It does not need to produce a discovery or a breakthrough or a revelation. It simply needs to keep happening. Because as long as someone, somewhere, is listening to the universe is, in some quiet sense, not alone. Neither are we. The cosmos is full of light and full of dark and full of mysteries that will outlast every name, every memory, every civilization that has ever tried to take its measure. We are the briefest part of it. The stars are older. The galaxies are older still. The universe itself is older than imagination. And yet, somehow, briefly, we are here, with Webb, with each other, with the slow accumulation of careful knowledge, with the night, and with the stars within it. May that company stay with you, however softly, into whatever comes next. May the long patience of the cosmos teach you, in small ways, the long patience of your own life. May you sleep, if you are sleeping, with the universe as a quiet companion, neither distant nor demanding, simply there, the way it has always been. And may you wake when you wake, with the smallest, gentlest awareness that the same universe Webb is studying is the same universe holding the chair you sit in, the air you breathe, the cells of the body that carries you. The cosmos is not somewhere far away. It is here, around you, inside you. Webb just helps us see it more clearly. That is its gift. And tonight, that gift has been yours. Take it gently with you into whatever the rest of this night becomes. There is one more thing worth saying, gently, before we let this evening end. When Webb returns its images to Earth, those images are not photographs in the way you might first imagine. Infrared light is invisible to the human eye. The colors you see in a Webb image, the gentle blues, the deep ambers, the soft reds, are translations. Astronomers assign visible colors to wavelengths your eyes could never have seen on their own. What you are looking at when you look at a Webb image is a kind of poem, a faithful translation of something whose original language your senses do not speak. The data is real. The structure is real. The galaxies are real. But the colors are a courtesy, a bridge built across the gap between what the universe is actually emitting and what your evolved biology happens to be tuned for. This is, in a quiet way, beautiful. It means that every public Webb image is a collaboration between two intelligences: the universe, which produces the light, and the humans who translate it into something the rest of us can hold in our minds. Without the translation, the data would remain locked inside numbers, accessible only to those who can read the spectra directly. With the translation, those numbers become images that anyone, anywhere, can carry in their pocket and pull out late at night when they cannot sleep. The translation is a gift. The translation is also a reminder. There are layers of reality your senses do not directly access. The visible light you see is a thin slice of an enormous spectrum. Beyond the red, there is infrared, then microwave, then radio, stretching to wavelengths longer than mountains. Beyond the violet, there is ultraviolet, then X-ray, then gamma, reaching frequencies that compress entire suns into fractions of a second. Your eye sees a narrow band in the middle. Your body responds to a slightly wider band, registering some infrared as warmth, some ultraviolet as sunburn. The rest passes through you, around you, past you, all the time, carrying information you have no native way to read. Webb reads some of that information. Other instruments read the rest. The full picture of the universe, when it is finally assembled, will not be a picture in any familiar sense. It will be something more like a chord, a sustained harmony of measurements across every wavelength, every kind of particle, every available method of listening. We are still tuning the instruments. We are still learning to hear.